Imagine a world born from fire and destruction. A planet not formed in the slow, delicate process that made Earth, but instead, one that emerged from the violent explosion of a dying star. Could something so chaotic, so devastating, actually create a new world? The idea sounds almost impossible. When a star explodes in a supernova, it rips itself apart with a force beyond comprehension. Everything in its path is vaporized, flung into space at insane speeds. The energy released can outshine an entire galaxy for weeks. It's destruction on the grandest scale. But here's the twist: what if that destruction wasn't the end? What if, hidden in the aftermath of a cosmic explosion, there were the building blocks of a brand new planet? Could supernova remnants, those clouds of gas, dust, and heavy elements, somehow come together and form something stable? Something solid? Something that could, against all odds, give rise to a new world? The idea of planets forming from supernova remnants challenges what we think we know about planetary formation. Traditional planet formation happens around young stars. A newborn star gathers a disk of dust and gas around it, and over millions of years, that disk gradually clumps together, forming planets. But a supernova is the opposite of that. It's the death of a star, not the birth. Instead of a stable, warm environment where particles can slowly stick together, you have a chaotic, high-energy explosion that tears everything apart. So how could a planet possibly form in such a scenario? It seems counterintuitive, but some scientists believe it's not only possible, it might have already happened. To understand this, let's break it down. When a massive star reaches the end of its life, it stops producing energy in its core. Without that outward pressure, gravity takes over and causes the star to collapse. This collapse triggers an explosion so powerful that it hurls the star's outer layers into space, spreading elements like carbon, oxygen, iron, and even gold into the cosmos. These are the ingredients that make up everything we know, including planets, moons, and even life itself. The question is, can these elements reorganize themselves into a new planet quickly enough before they disperse into space? Some astronomers have proposed that under the right conditions, the shock waves from a supernova could compress certain areas of the ejected material, causing it to clump together instead of scattering apart. If enough mass gathers in one place, gravity could start pulling in more debris, slowly forming something solid. Over time, this could grow into a planet-like object. But there are a lot of challenges to this idea. First, the environment around a supernova is incredibly hostile. Any newly forming object would have to withstand intense radiation, high-speed particles, and gravitational disturbances from nearby stars. It's not exactly the kind of place you'd expect something as delicate as a planet to come together. Yet, despite these challenges, some researchers believe there is evidence that supernova-born planets might exist. Observations of certain exoplanets, planets outside our solar system, suggest that some of them contain elements that are typically found in supernova remnants. This raises the possibility that at least some planets might have formed in ways we never expected. Instead of forming in a peaceful, orderly disk around a young star, these planets could have been forged in the violent aftermath of a cosmic explosion. And there's another twist to this story. Some scientists think that instead of forming entirely from supernova remnants, some planets could have started as normal planets orbiting a star that later exploded. When the star went supernova, these planets would have been thrown into chaos. Some might have been completely destroyed. Others might have been blasted into interstellar space, becoming rogue planets, wandering alone in the darkness, no longer bound to any star. But a few, under the right conditions, might have actually survived and even picked up new material from the explosion, changing their composition entirely. This raises a fascinating question: could there be planets out there that have witnessed the death of their own sun? Imagine a world that once had a sky filled with the warm light of a massive star, only to see that star swell, turn red, and explode in a supernova. If any life had developed on such a planet, it would have witnessed an apocalypse beyond anything we can imagine. And yet, after the explosion, if the planet somehow remained intact, it might have continued drifting through space, forever marked by the destruction it survived. One of the most interesting candidates for this kind of scenario is a group of planets known as Pulsar planets. These are planets that orbit pulsars, dead remnants of massive stars that exploded in supernovae. Pulsars are some of the strangest objects in the universe. They are neutron stars, incredibly dense remnants of supernovae that spin rapidly, emitting beams of radiation like cosmic lighthouses. The fact that planets have been found orbiting these bizarre objects suggests that at least some planetary material can survive the chaos of a supernova. But were these planets formed before or after the explosion? That's still a mystery. Some scientists think that pulsar planets formed after the supernova, using leftover material that didn't escape into space. Others believe they were already there before the explosion and somehow managed to survive. Either way, their existence proves that planets can exist in places we never expected. If planets can orbit pulsars, could they also form directly from supernova remnants? That's a question researchers are still trying to answer. To understand whether this is truly possible, scientists have studied the chemical makeup of certain exoplanets. Some planets have been found with unusually high amounts of heavy elements that are typically created in supernova explosions. This suggests that at least some planets have incorporated material from past supernovae into their composition. But does that mean they were entirely formed from supernova debris, or did they just pick up some of that material later? That's still an open question. Another factor to consider is the role of supernova shockwaves. When a supernova explodes, the shockwave it produces can trigger star formation in nearby clouds of gas. In some cases, this could also lead to planet formation. If a dense region of debris left over from a supernova were to experience a secondary collapse due to one of these shockwaves, it's possible that a new planet could start forming inside it. This would be a completely different process from the traditional planet formation we see around young stars, but it might explain some of the strange, heavy element-rich planets we've discovered. Ultimately, the idea of planets forming from supernova remnants is still just that, an idea. There's no definitive proof yet, but the more we learn about the universe, the more we realize that planetary formation might be more diverse than we ever imagined. Planets might not always need a calm, stable environment to form. Some might emerge from destruction, proving that even in the aftermath of a cosmic apocalypse, new worlds can rise. The idea that planets could form from supernova remnants is one of the most fascinating and counterintuitive possibilities in astrophysics. Traditionally, we think of planet formation as a slow and steady process, happening in the relatively peaceful environment of a protoplanetary disk surrounding a young star. But what happens when a planet has no such stable environment? What if, instead of forming in the glow of a newborn star, it takes shape in the aftermath of a dying one? If planets can truly form from supernova debris, that would mean entire worlds could exist that owed their origin to destruction itself. To explore this further, let's look at what exactly is left behind after a supernova. When a massive star explodes, it doesn't just send out random clouds of dust and gas. It releases a specific mix of heavy elements that can tell us a lot about its history. Unlike the early universe, which was mostly hydrogen and helium, supernovae spread elements like iron, carbon, oxygen, silicon, and even uranium into space. These are the same elements that make up rocky planets, including Earth. In fact, everything on Earth, including our own bodies, is made from elements forged in ancient supernovae. That alone suggests that planetary material can come from stellar explosions. But the real question is whether planets can form directly in the chaotic aftermath of one. One major problem with this idea is that supernova remnants don't behave like the disks of dust and gas around young stars. A protoplanetary disk is relatively cool and stable, allowing small particles to slowly stick together over time. A supernova remnant, on the other hand, is an expanding cloud of gas and dust moving outward at extreme speeds. Instead of gently drifting toward each other and forming clumps, the material in a supernova remnant is often blasted apart by high-energy radiation and violent turbulence. That makes it hard for any planetary material to stay together long enough to form something solid. However, there are scenarios in which this could work. If the supernova occurs in a dense region of space, such as a molecular cloud, the material from the explosion might not be able to disperse as easily. Instead of expanding indefinitely, some of it could be slowed down by surrounding gas and dust, allowing pockets of matter to start clumping together. This is where gravity comes into play. If enough mass gathers in one place, gravity could start pulling in more and more material, eventually leading to the formation of a planet-like object. But even if this happens, would the resulting object be a real planet? That depends on the definition. A planet is usually considered to be a body that orbits a star and has cleared its orbit of debris. A planet forming directly from supernova remnants might not have a stable orbit around anything. It could be a free-floating rogue planet, drifting through space with no home. Rogue planets are already a known phenomenon, with some estimates suggesting there could be billions of them in the Milky Way alone. If supernova remnants can create planets, they might be responsible for some of these wandering worlds. Another clue that supports this idea comes from the study of white dwarf stars. White dwarfs are the leftover cores of stars that were once similar to our Sun. Some white dwarfs have been found with planetary debris around them, suggesting that planets can exist in systems that have undergone violent changes. If planets can survive the transformation of their star into a white dwarf, could similar survival, or even formation, happen around a neutron star or black hole left behind by a supernova? This brings us back to pulsar planets. The first confirmed discovery of exoplanets was around the Pulsar, PSR B1257+12, in the early 1990s. These planets orbit a neutron star, which is the dense, collapsed core of a massive star that exploded in a supernova. The existence of these planets was shocking because pulsars are incredibly hostile environments, bombarding anything nearby with intense radiation. How did these planets get there? Did they survive the supernova that created the pulsar, or did they form afterward? One possibility is that these planets formed from a disk of material left behind after the supernova. If a supernova explosion wasn't completely symmetrical, some of the debris might not have been blown away entirely. Instead, some of it could have remained in orbit around the newly formed neutron star, eventually forming a disk similar to a protoplanetary disk around a young star. Over time, that disk could have given rise to planets, just like in a more traditional planetary system. If this is true, then planets forming from supernova remnants might not be as rare as we think. Instead of being one in a billion occurrences, they could be a natural part of the cosmic life cycle, an unexpected but real pathway for planet formation. If that's the case, it means there could be planets out there that were never part of a normal solar system. Instead, they might have been born in the wreckage of a destroyed star, forming in the shadow of a supernova and orbiting a dead stellar core. But what would a planet like this actually look like? Would it be anything like Earth? Probably not. For one, the radiation environment near a neutron star or black hole is extreme, making it unlikely that such a planet would have an atmosphere like ours. If it were a rocky planet, it might be covered in strange minerals formed from supernova debris. If it were a gas giant, its atmosphere might be rich in unusual elements, possibly containing exotic chemicals that don't exist on planets formed in traditional protoplanetary disks. And then there's the question of habitability. Could life exist on a planet formed from supernova remnants? At first glance, the answer seems to be a clear no. After all, these planets would be born in some of the most extreme environments in the universe. But if science has taught us anything, it's that life finds ways to adapt in places we never expected. On Earth, life has been found in deep-sea hydrothermal vents, in acidic lakes, and even inside nuclear reactors. If a supernova-born planet had the right conditions, such as underground oceans protected from radiation, it's not impossible that life could exist there, even in some primitive form. There's also the possibility that such a planet could have once been habitable, but was later devastated by the supernova that created it. Imagine an advanced civilization developing on a planet orbiting a massive star. For millions of years, they thrive, unaware that their star is nearing the end of its life. Then, one day, the star goes supernova. If the explosion doesn't completely destroy the planet, it would still be a catastrophic event, stripping away the atmosphere and bombarding the surface with deadly radiation. If any life survived, it would have to adapt to an entirely new world, a world shaped by fire and destruction. So, could planets form from supernova remnants? The answer is still uncertain, but the evidence suggests it might be possible. Whether it's through direct formation in a debris cloud, the survival of pre-existing planets, or the capture of material into a new planetary system, there are multiple pathways that could lead to the existence of these strange worlds. If they do exist, they would be some of the most extreme planets in the universe, worlds born from explosions, forged in chaos, and shaped by the violent death of a star. And if that's true, it means something incredible. Even in the most destructive forces of the universe, there is still the potential for creation. Destruction isn't always the end. Sometimes, it's just the beginning of something new. The idea that destruction can give birth to something new is one of the most profound concepts in the universe. If planets can form from the remnants of supernovae, then the cosmos is even more dynamic than we ever imagined. It means that the ashes of dead stars don't just scatter into nothingness. They reorganize, reform, and create new worlds that might one day host life. This raises even more fascinating questions. How common could these planets be? Could they be detected? And if they do exist, what could they tell us about the universe's ability to recycle itself in ways we never expected? One of the biggest challenges in studying this possibility is actually finding these planets. Detecting planets around normal stars is already difficult, but trying to spot one around a neutron star or in a supernova remnant is an entirely different challenge. Traditional planet hunting methods rely on either observing a planet's gravitational effect on its star or detecting the tiny dip in brightness when a planet passes in front of its star. Neither of these methods works well for planets in supernova remnants, because these remnants are often chaotic and don't emit steady, detectable light like a main sequence star does. However, astronomers have found some potential workarounds. One way to detect planets near neutron stars or pulsars is by looking at the timing of their pulses. Pulsars emit beams of radiation at incredibly precise intervals, acting like cosmic lighthouses. If a planet is orbiting a pulsar, its gravitational influence can slightly change the timing of these pulses. This is how the first confirmed exoplanets were found around Pulsar B1257+12 in the 1990s. If more planets like this exist, it might be possible to find them using similar methods. But what about planets that don't orbit anything, rogue planets that form directly from supernova debris and now drift through space? These would be even harder to find. Some rogue planets have been detected by their gravitational lensing effect, when their gravity slightly bends and magnifies the light of a background star. But this method is rare and only works in specific cases. If most supernova-born planets are rogue, they could be out there in huge numbers, completely undetectable unless they happen to pass in front of a distant light source. This raises another question: how many of these planets could exist? If even a small percentage of supernova remnants lead to planet formation, the number could be staggering. The Milky Way alone has seen countless supernovae throughout its history, meaning there could be billions of planets that were born from the explosions of dying stars. Some of them might be orbiting pulsars, others might be free-floating, and some might have even been captured by other star systems over time, blending into planetary systems in ways we don't yet understand. One of the most mind-bending ideas is that Earth itself could contain material from one of these planets. Since our solar system formed from an ancient cloud of gas and dust, which itself was enriched by past supernovae, it's possible that some of the material in our planet originally belonged to a world that existed before our sun was even born. If true, it would mean that planets aren't just created and destroyed. They merge, mix, and evolve over time, creating a deep cosmic lineage that connects worlds across billions of years. If planets formed from supernova remnants exist, they could be some of the strangest places in the universe. Unlike typical planets, which form in the relatively calm environments of protoplanetary disks, these worlds would have formed under extreme conditions. The radiation levels would have been immense, the temperatures would have been chaotic, and the chemical composition might be completely different from what we see in normal planetary systems. Some of these planets might be rich in exotic elements that are rare on Earth. Supernovae are responsible for creating many of the heavy elements in the universe, including gold, platinum, and uranium. A planet that formed directly from supernova debris could have unusual mineral deposits, strange surface features, or even entirely unknown types of chemistry. If we ever discovered one of these planets up close, it could redefine our understanding of planetary formation and even materials science. Another bizarre possibility is that some of these planets might have magnetic fields stronger than anything we've seen before. Pulsars and neutron stars have incredibly powerful magnetic fields. Some are billions of times stronger than Earth's. If a planet formed near one of these objects, it might have absorbed some of the extreme magnetic properties of its environment. This could lead to a world with strange electromagnetic effects, possibly influencing its atmosphere or even generating bizarre auroras unlike anything we see on Earth. And then there's the question of habitability. At first glance, these planets seem like the last places where life could exist. But the universe has a way of surprising us. If a planet formed in a supernova remnant, but eventually drifted into a more stable environment, it might have had time to develop conditions suitable for life. If it had water or an atmosphere that could protect it from radiation, microbial life might have had a chance to take hold. There's even a possibility that intelligent life could one day arise on a planet formed from supernova remnants. Imagine an advanced civilization living on a world made from the debris of a long-dead star, looking up at the sky and wondering where they came from. If such civilizations exist, they might have a completely different understanding of the universe than we do. To them, supernovae wouldn't just be distant cosmic events, they would be the reason their planet exists. If we ever discover one of these planets, it could answer some of the biggest questions in astronomy. It could show us how the universe recycles itself, how destruction leads to creation, and how even the most violent events can give rise to new possibilities. It would prove that planets don't just form in the traditional way we've always assumed, but can emerge from chaos itself. This brings us back to the deeper philosophical question at the heart of all this. If planets can form from supernova remnants, what does that say about the nature of the universe? It suggests that nothing is ever truly lost. Even the most powerful explosions in the cosmos don't erase everything, they create the building blocks for something new. In a way, this mirrors the cycle of life and death we see in nature. Just as forests regrow after wildfires and life adapts after extinctions, the universe itself finds ways to rebuild after destruction. The possibility of planets forming from supernova remnants is more than just an interesting scientific question. It's a reminder that the cosmos is full of surprises, that even in destruction there is creation, and that the story of the universe is far more intricate than we ever imagined. The next time you look up at the night sky, remember that some of the stars you see will one day explode, and in their wake, new worlds may form, waiting for someone to discover them. If planets can form from the remains of supernovae, then the universe is even more unpredictable than we thought. This means that every explosion, every burst of energy, and every piece of stellar debris could be part of a larger cosmic cycle. It forces us to rethink the very nature of planetary formation. Instead of being a simple process tied to star birth, it could also be something that happens in the aftermath of stellar death. But how often does this actually occur? And what would it mean for our understanding of planetary systems as a whole? To begin answering these questions, let's consider the raw materials left behind after a supernova. A supernova doesn't just scatter elements randomly, it spreads them in a structured way, with heavier elements staying closer to the center and lighter ones being pushed farther out. This means that any planet forming from supernova debris would likely have a very different composition compared to planets that formed in a regular protoplanetary disk. Some of these planets could be extremely rich in heavy elements like gold, platinum, and uranium, while others might be almost entirely made of carbon, iron, or other materials that were abundant in the explosion. This raises an interesting possibility. Could a planet form almost entirely out of rare or valuable elements? We often think of planets as being made mostly of rock, gas, or ice, but what if a planet existed that was primarily composed of metals like platinum or gold? Theoretically, if the conditions were just right, an entire planet could form with an unusual concentration of these elements. If such a world were discovered, it would not only be a scientific marvel but also a target of immense interest for space exploration. The idea of a gold planet might sound like science fiction, but in a universe filled with extreme conditions, it might not be impossible. But let's take this idea a step further. If a planet can form in a supernova remnant, could it also form inside the remnant before it fully disperses? The early stages of a supernova remnant are incredibly chaotic, filled with high-energy radiation, shock waves, and intense temperatures. However, over time, things begin to settle. If enough material clumps together in the right way, it's possible that small planetary bodies could begin forming even before the remnant fully fades away. These objects would experience some of the most extreme conditions imaginable, yet if they survived, they might become some of the oldest planets in the universe. And this leads to another mind-boggling question: could there be planets out there that are billions of years older than any known exoplanets? If planets can form in supernova remnants, then they could have started forming much earlier in the history of the universe than previously believed. Some might be older than the Milky Way itself, drifting through intergalactic space as ancient relics from the earliest generations of stars. If we ever find one of these ancient planets, it could tell us more about the first stars, the first galaxies, and even the origins of the elements that make up our own world. But how would these planets evolve over time? Unlike planets that form around stable stars, these worlds would start their existence in an incredibly violent environment. Radiation from the remaining neutron star or pulsar could strip away atmospheres, while high-energy particles could drastically alter their surfaces. If any of these planets had the potential for life, it would have to be extraordinarily resilient. However, if the planet eventually moved into a more stable environment, perhaps drifting into the orbit of a calmer star, it might have a chance to develop more Earth-like conditions. This brings up yet another fascinating thought. Could a planet formed from supernova debris end up hosting life billions of years later? If a planet started out in a hostile environment but later entered a more habitable zone, life might have a chance to develop in ways we've never considered. It's even possible that some of the most extreme planets in the universe could one day become cradles of life under the right conditions. This means that life could emerge in places we would never think to look, in the aftermath of destruction, in the chaos of a supernova remnant, and in the lingering dust of dead stars. If we could visit one of these planets, what would we see? The surface might be unlike anything we've encountered before. The mineral composition would likely be vastly different from Earth's, and the atmospheric conditions, if an atmosphere existed, could be wildly unpredictable. The sky might be filled with strange auroras caused by leftover magnetic activity, and the terrain might be rich with elements we rarely find on our own planet. If there were mountains, they might be made of pure metal rather than rock. If there were seas, they might contain liquid substances that don't exist naturally on Earth. And if life did develop, how would it adapt to such an environment? On Earth, life has evolved to survive under a wide range of conditions, from deep-sea hydrothermal vents to the frozen wastelands of Antarctica. But on a supernova-born planet, the conditions might be so extreme that life would have to develop entirely new biological structures. Perhaps organisms would evolve natural radiation shielding, or maybe they would harness the extreme magnetic fields for energy. If intelligent life ever emerged on one of these planets, their entire perception of the universe might be different from ours. Instead of fearing supernovae, they might revere them as the very events that made their existence possible. Could we ever detect one of these planets for sure? Finding planets around normal stars is already a huge challenge, so detecting a planet in a supernova remnant would be even harder. However, as technology advances, new detection methods might make it possible. Future telescopes could be designed to scan supernova remnants for any hints of planetary formation. If even one of these planets were found, it would revolutionize our understanding of how the universe builds itself from destruction. And what about rogue planets? Planets that formed from supernova debris and were ejected into interstellar space. These planets could be drifting unseen between the stars, carrying with them the secrets of their violent origins. If we ever encounter one of these rogue planets up close, it could be like opening a time capsule from an ancient cosmic explosion. The materials on its surface could reveal details about the specific supernova that created it, and its core composition could tell us more about how planets can form under the most extreme conditions. In the grand scheme of things, this possibility reshapes how we view the life cycle of the universe. We often think of supernovae as the dramatic, fiery deaths of stars, but what if they're also part of the process of rebirth? What if every explosion is not just an end, but also a beginning? If planets can form from supernova remnants, then the cosmos is far more interconnected than we ever realized. Every atom in our bodies was forged in the heart of a star, but some atoms may have come from planets that existed long before Earth was even formed. The idea that planets can emerge from the ashes of dying stars suggests that the universe never wastes anything. It takes destruction and turns it into creation, over and over again, for billions of years. This means that somewhere out there, right now, new planets could be forming from the wreckage of ancient supernovae. Some of them might remain lifeless forever, drifting through space as silent relics of destruction. But others might one day become something more: a home, a world with oceans and skies, or even a place where life takes its first steps. The universe is full of mysteries, but if there's one thing we can be certain of, it's that nothing ever truly ends. Even the most violent explosions can give birth to something new. If supernovae can give rise to new planets, then the cycle of stellar life and death becomes even more complex than we ever imagined. The universe is not just a place where stars are born, live, and die. It's a place where even the wreckage of destruction has the potential to create something entirely new. This idea challenges the way we think about planetary formation. Traditionally, we believe planets emerge from the protoplanetary disks that surround young stars. But if planets can also form from the remnants of dead stars, then planetary formation is not a one-way street. It's a process that can happen in multiple ways, under vastly different conditions. To fully understand this, we need to consider how planets normally form. In a traditional star system, a cloud of gas and dust collapses under gravity, and a star begins to take shape at the center. Around this forming star, leftover material flattens into a rotating disk. Over time, small particles stick together, forming larger and larger bodies. Eventually, these bodies grow massive enough to become planets, moons, asteroids, and comets. This is the standard model of planetary formation. But in a supernova remnant, the conditions are entirely different. There is no stable protoplanetary disk. Instead, there's a violent, expanding cloud of gas and debris, filled with radiation, high-energy particles, and extreme magnetic fields. At first glance, this seems like an impossible environment for planet formation. But as the explosion settles, some regions of the remnant could begin to cool and collapse under their own gravity. If these regions contain enough solid material, they might start forming planetary bodies. These planets would be fundamentally different from those that form around young stars. Instead of having long, gradual formation periods, they might come together rapidly as clumps of material collide in the chaotic aftermath of the explosion. The composition of these planets would also be highly unusual. While normal planets form from a mix of elements present in the original nebula, supernova-born planets would be rich in elements forged during the star's final moments. These could include heavy metals like gold, platinum, and uranium, elements that are rare in most planetary systems. One of the biggest challenges to this idea is the role of radiation. A supernova remnant is an incredibly hostile place, filled with intense X-rays, gamma rays, and charged particles. This radiation could make it difficult for solid bodies to form and persist. However, if some regions of the remnant are shielded from the worst of this radiation, perhaps in dense clumps of gas and dust, then small planetary embryos might have a chance to grow. Over time, these planetary seeds could accumulate more material and eventually form full-fledged planets. But what happens next? A planet forming in a supernova remnant wouldn't have a parent star in the traditional sense. Instead, it might be left drifting through space as a rogue planet, unattached to any star. These planets could travel through the galaxy, carrying the chemical signatures of the explosion that created them. If they eventually enter the gravitational pull of another star system, they might settle into orbit and become part of an entirely different planetary system. This means that some of the exoplanets we discover today could have origins we never expected. They might not have formed with their current stars at all, but instead were born from ancient stellar explosions and later captured by new star systems. This raises a wild possibility. Could our own solar system contain a planet that originally formed from a supernova remnant? While all planets in our solar system likely formed from the same protoplanetary disk, it's not impossible that a rogue planet could have been captured by the Sun's gravity at some point in the past. If this ever happened, that planet would carry chemical fingerprints very different from the rest of the solar system, possibly revealing an origin tied to a long-dead star. But if supernova-born planets exist, how would we detect them? Right now, most exoplanets are discovered using the transit method, when a planet passes in front of its star and dims its light, or the radial velocity method, when a planet's gravity causes its star to wobble. Neither of these methods would work for a planet that isn't orbiting a star. However, astronomers have recently discovered rogue planets drifting through the galaxy by using gravitational microlensing, a technique that detects planets by observing how their gravity bends the light of background stars. If supernova-born planets exist, they might be hiding among the rogue planets we've already detected, just waiting for us to analyze their composition and find the telltale signs of their unusual origins. Another way to identify these planets would be through their chemical makeup. If a planet formed from a supernova remnant, it would likely have much higher concentrations of certain heavy elements compared to planets that formed in regular protoplanetary disks. Future telescopes might be able to analyze the atmospheres or surfaces of rogue planets to see if they contain unexpected levels of elements like iron, gold, or even radioactive isotopes that point to a supernova origin. If we could visit one of these planets, what would it be like? Would it be a desolate wasteland scarred by the violence of its birth? Or could it have developed conditions that support life? If the planet retained any atmosphere, it might be thick with exotic gases that don't exist in large amounts on Earth. Its surface could be covered in strange mineral formations, possibly even metals that glisten under an alien sky. If the planet somehow managed to hold onto water or other liquids, it could have bizarre, chemical-rich oceans unlike anything we've seen before. And if life did develop there, what kind of adaptations would it have? Would it be resistant to radiation, having evolved under the lingering effects of the explosion? Would it metabolize heavy metals instead of carbon-based nutrients? Could it even possess biological structures that incorporate elements we don't associate with life at all? These are the kinds of questions that push the boundaries of what we think is possible. If supernova remnants can give birth to planets, then the universe is far more dynamic than we ever thought. It suggests that planetary formation isn't just something that happens in the quiet disks around young stars. It can also emerge from the ashes of stellar destruction. And this has an even deeper implication. It means that the death of a star is never truly the end. Even the most violent explosions, the most chaotic bursts of energy, can eventually give rise to something new. Planets that form from supernova remnants might one day become homes for life. They might orbit new stars billions of years after their original stars died. They might drift through the galaxy, carrying the history of their past within their cores. Somewhere out there, right now, a planet could be forming from the remains of a star that exploded millions of years ago. Maybe one day, we'll find it. Maybe one day, we'll step onto its surface and realize that even in destruction, the universe always finds a way to create something new. The idea that planets could emerge from the wreckage of a dead star isn't just a theoretical curiosity. It fundamentally changes how we understand the universe. For centuries, humanity has viewed supernovae as endpoints, the final, cataclysmic moments in a star's life. But what if they're not just endings? What if they're also beginnings? The implications stretch far beyond just planetary formation. If planets can arise from supernova remnants, then the life cycle of celestial bodies is far more complex and interconnected than we ever imagined. To understand the full significance of this possibility, we need to dive deeper into the mechanics of a supernova. When a massive star reaches the end of its life, it burns through its fuel at an accelerated rate, fusing lighter elements into heavier ones. At some point, the fusion process reaches iron, which is where everything changes. Unlike previous elements, iron doesn't generate energy when fused, it absorbs it. This leads to a sudden loss of outward pressure, causing the core of the star to collapse under its own immense gravity. The result? A violent explosion that scatters the star's outer layers across space, unleashing more energy in a matter of seconds than our Sun will produce in its entire 10 billion-year lifetime. The debris left behind in the aftermath of this explosion is what we call a supernova remnant. It's a chaotic mix of high-energy particles, radiation, and heavy elements forged in the dying moments of the star's life. If a neutron star or black hole forms at the center, it continues to emit powerful magnetic fields and radiation that interact with the surrounding debris. At first, this environment seems utterly inhospitable to planetary formation. But as the remnant expands and cools, small regions of material might begin to coalesce under their own gravity. What's fascinating is that supernova remnants are rich in elements that are critical for planet building. Our own Earth, for example, contains significant amounts of iron, nickel, and other heavy metals, elements that were forged in past supernovae. This means that every planet we know of, including Earth, is in some way a product of stellar death. But the idea that entire planets could form directly within the remnants of a single supernova means that some worlds might have entirely different chemical compositions than anything we've seen before. Imagine a planet where nearly the entire crust is composed of rare metals, where the mountains are made of platinum and the rivers flow with mercury like liquid metals. The atmosphere, if it exists, could be infused with exotic gases that were expelled in the explosion, creating conditions completely alien to anything on Earth. The magnetic fields generated by a nearby neutron star could create auroras that stretch across the entire sky, illuminating the surface with eerie, shifting lights. One of the biggest challenges in proving that supernova-born planets exist is figuring out how to detect them. The planets we've discovered so far have mostly been found orbiting stars, but a planet forming within a supernova remnant might not have a parent star at all. These planets could be rogue, drifting alone through interstellar space, carrying with them the chemical signatures of their violent origins. Rogue planets have already been detected using gravitational microlensing, a technique that relies on the bending of light around massive objects. But identifying one that specifically came from a supernova remnant would require looking at its elemental composition. If astronomers could analyze the atmosphere or surface of such a planet and find an unusual abundance of heavy elements, it might provide the first concrete evidence that planets can form from the debris of dying stars. Another possibility is that some of these planets might eventually be captured by other star systems. If a rogue planet drifts close enough to a young star, it could be pulled into orbit and become part of a completely new planetary system. This raises a fascinating question. Could some of the exoplanets we've already discovered have originated not from the stars they currently orbit, but from ancient supernovae? If this is true, then planetary formation isn't just something that happens in a single location. It's a process that can happen, stop, and restart across vast cosmic distances. A planet that was born in the chaotic wreckage of an exploding star might, billions of years later, find itself orbiting a completely unrelated star, playing host to new possibilities, maybe even life. And speaking of life, could anything actually survive on a planet born from a supernova remnant? At first glance, the idea seems unlikely. The radiation levels in the early stages of formation would be extreme, and any life that might emerge would have to be incredibly resistant to radiation. But if the planet cooled and formed a stable atmosphere, life could theoretically develop in ways that we can barely begin to imagine. Could we find organisms that metabolize heavy metals instead of organic compounds? Could life develop in environments filled with exotic gases that are toxic to us but essential for alien biochemistry? These are questions that push the boundaries of what we consider possible. If planets can form from supernova remnants, then life itself might be more adaptable than we've ever believed. Perhaps the most exciting part of this idea is that it suggests the universe is even more dynamic than we thought. Destruction leads to creation, and the death of one star might set the stage for entirely new worlds. Somewhere out there, a planet formed from a supernova might be waiting for discovery, an ancient, wandering world carrying the echoes of a long-dead star. And maybe, just maybe, that world holds secrets that could change everything we know about the cosmos. If planets forming from supernova remnants is possible, then the universe might be full of orphaned worlds, drifting alone, forged from the remains of long-dead stars. But just how likely is this process? To answer that, we have to break down the key factors that influence planetary formation and see whether the conditions within a supernova remnant could actually support them. First, let's consider the primary requirement: raw material. A supernova ejects massive amounts of heavy elements, including iron, nickel, silicon, and carbon, materials that are essential for building rocky planets. In fact, without supernovae, planets like Earth wouldn't exist at all. The iron core of our planet, the gold in our jewelry, and even the calcium in our bones were all formed in the final moments of ancient stellar explosions. The difference here is that in traditional planetary formation, these materials mix into vast molecular clouds that later collapse to form new star systems. But if planets were to form directly inside a supernova remnant, the process would be much more chaotic. One major challenge is the intense radiation environment. When a star explodes, it releases an immense amount of X-rays and gamma rays, along with a powerful shockwave that sweeps through the surrounding space. This shockwave can reach speeds of tens of thousands of kilometers per second, blasting apart anything in its path. Any material attempting to clump together into a planet would be constantly bombarded by high-energy radiation, making it difficult for solid bodies to form. However, as the remnant expands and cools over thousands or even millions of years, the radiation levels drop. This creates a potential window where dust and debris could begin to stick together and form larger objects. Another factor to consider is gravity. In a typical planetary system, a central star provides the gravitational anchor that helps material coalesce into planets. Without a central star, how would the dust and debris come together? One possibility is that the remnant of the original star, a neutron star or a black hole, could exert enough gravitational influence to help pull material together. Neutron stars, in particular, have incredibly strong magnetic fields that could shape the surrounding matter into dense clumps, potentially serving as seeds for planetary formation. There's also the possibility that some supernova remnants retain dense regions of gas that weren't completely blown away in the explosion. If these gas pockets survive long enough, they could act as nurseries for planetary growth. Observations of some supernova remnants have revealed clumps of material that seem to be gravitationally bound, suggesting that at least some degree of structure can emerge within these chaotic environments. But here's where things get really interesting. What if some of these planets form not as solid, rocky worlds, but as entirely new types of celestial objects? The extreme conditions of a supernova remnant could lead to the creation of planets unlike anything we've ever seen. Planets with cores made almost entirely of heavy metals, or planets with surfaces covered in thick layers of exotic, high-pressure ice. Some of these worlds might be so dense that they resemble miniature versions of neutron stars, with gravity so strong that it bends light around them. Others might be composed almost entirely of carbon, forming massive diamond-like structures floating through space. Detecting such planets would be a major challenge. Most of the exoplanets we've discovered so far have been found by looking for dips in a star's brightness when a planet passes in front of it, a method called the transit technique. But a planet formed in a supernova remnant might not have a parent star at all, making it effectively invisible to traditional detection methods. The best way to find these rogue planets might be through gravitational microlensing, which occurs when a massive object passes in front of a distant star and bends its light. This technique has already been used to detect rogue planets, so it's possible that some of the objects we've found using this method are actually remnants of supernova-born worlds. If we could study one of these planets up close, the data could provide groundbreaking insights into planetary formation and the long-term effects of supernova explosions. Could these planets retain any traces of their parent star's original composition? Would their atmospheres, if they had any, contain elements that are typically rare in traditional planetary systems? And perhaps the most intriguing question of all, could life ever exist on such a world? At first glance, the idea seems absurd. A planet formed in the aftermath of a supernova would be one of the most hostile environments imaginable, bombarded by radiation and stripped of any protective atmosphere. But given enough time, could conditions stabilize enough for some form of life to emerge? If extremophiles on Earth can survive in deep-sea hydrothermal vents, acidic lakes, and even radioactive waste sites, could similar life forms adapt to the harsh conditions of a supernova remnant planet? There's also the possibility that life could take a completely different form. If a planet's chemistry is dominated by heavy elements rather than the lighter elements we associate with life, like carbon, hydrogen, and oxygen, could that give rise to an entirely new biological framework? Could we see organisms that metabolize metals instead of organic compounds, or creatures that rely on superconducting materials for neural activity? The possibilities push the boundaries of what we consider life to be. The search for supernova-born planets is still in its early stages, but if they exist, they could revolutionize our understanding of the universe. These planets would be living proof that destruction leads to creation, that the end of a star's life doesn't have to mean the end of its story. Instead, it could mark the beginning of something entirely new, a world forged in fire, carrying the echoes of a cosmic explosion. And if one of these planets has survived for billions of years, drifting through space, waiting to be discovered, what secrets might it hold? Could it carry traces of its parent star, locked away in its crust? Could it have been captured by another star system, unknowingly blending into a planetary family that wasn't its own? Or could it be out there right now, completely alone, a silent witness to the violent forces that created it? The universe is full of surprises, and as our technology improves, we may one day uncover evidence that planets can indeed form from supernova remnants. And when that day comes, it will force us to rethink everything we thought we knew about how worlds are born. Because in the end, space isn't just a place of destruction, it's a place of endless creation, where even the death of a star can set the stage for new and unimaginable beginnings. The idea of planets forming from supernova remnants challenges our understanding of planetary evolution. We typically think of planets as forming within stable, well-structured protoplanetary disks around young stars, where dust and gas slowly come together over millions of years. But if planets could emerge from the chaos of a supernova explosion, it would mean that planet formation is a far more diverse and unpredictable process than we ever imagined. It would suggest that planets don't just form within the calm nurseries of stellar systems, but could also be born in the most violent and destructive environments the universe has to offer. If we consider how planets form in traditional settings, it becomes clear that there are some major obstacles to forming them from supernova debris. In a normal protoplanetary disk, dust grains collide and stick together, gradually building up into pebbles, then rocks, then planetesimals, and eventually full-fledged planets. The reason this process works is because these disks provide a relatively stable and low-energy environment where small particles can slowly accumulate over time. Supernova remnants, on the other hand, are anything but stable. The explosion sends material flying outward at speeds of thousands of kilometers per second, creating a hot, turbulent environment filled with high-energy radiation. Under such extreme conditions, it seems almost impossible for tiny dust grains to peacefully come together and form larger bodies. However, nature has a way of finding solutions in even the most unlikely circumstances. Some researchers suggest that as the supernova remnant expands and cools, certain regions might become dense enough for dust and gas to clump together. If these pockets of material can survive the intense radiation long enough, they might form structures similar to the early stages of protoplanetary disks. Instead of being orbitally bound to a central star, these disks would exist as isolated pockets of material floating through space. If enough mass collects in one of these regions, gravitational forces could take over, pulling in more debris and slowly shaping a planetary body. This raises another interesting question: how big could these planets get? In a typical solar system, planet size is largely determined by the amount of available material and the gravitational influence of nearby bodies. In a supernova remnant, there wouldn't be a central star to impose order, meaning that planet formation could be a much more chaotic process. Some of these worlds might never grow beyond the size of asteroids, remaining as drifting chunks of rock and metal. Others, if they gather enough mass, could become full-sized planets, potentially reaching sizes comparable to Earth or even larger. One particularly intriguing possibility is that some of these planets could become rogue super-Earths, massive rocky planets wandering the galaxy without a host star. If this happens, these worlds might resemble the giant metal-rich planets we've discovered around certain pulsars. In fact, some of the known pulsar planets, such as those orbiting the neutron star Pulsar B1257+12, might have originally formed from supernova remnants. These planets are thought to be rich in heavy elements, and may have formed in ways completely different from the planets in our solar system. If these planets exist, what would they be like? Would they have atmospheres? Could they have magnetic fields? One of the biggest challenges for a planet formed in a supernova remnant is retaining an atmosphere. Without a nearby star to provide warmth and stability, any gas surrounding the planet would likely be stripped away by the powerful stellar winds and radiation produced by the explosion. However, if the planet formed quickly enough, it might be able to hold onto some of its original atmosphere. Over time, it could develop a thick layer of gases, potentially composed of exotic elements not commonly found in traditional planetary atmospheres. Another factor to consider is the potential for liquid water. In our solar system, water exists in stable liquid form because Earth orbits within the habitable zone of the Sun. A rogue planet drifting through space wouldn't have that advantage. However, if the planet has a thick enough atmosphere, it might be able to trap heat through a strong greenhouse effect, keeping its surface warm enough for liquid water to exist. Alternatively, the planet's interior could contain a heat source, such as radioactive decay or tidal heating from interactions with a nearby object, allowing subsurface oceans to remain liquid beneath a frozen surface. But perhaps the most mind-blowing possibility is that some of these planets could be made almost entirely of heavy elements. We know that supernovae produce a wide variety of metals, including iron, gold, and platinum. If a planet formed directly from this material, it could have a composition completely unlike anything we've seen before. Imagine a planet with a core made almost entirely of iron, surrounded by a thick crust of nickel and silicate rock. Or a world where vast deposits of rare metals cover the surface, making it one of the most valuable objects in the universe. Some researchers have even speculated that planets with extremely high metal content might have unique properties, such as stronger magnetic fields or unusual geologic activity. There's also the question of what happens to these planets over time. If they start as free-floating objects, could they eventually get captured by a star and become part of a new solar system? This is certainly possible. Our galaxy is filled with wandering objects, and interactions between celestial bodies can sometimes lead to unexpected gravitational captures. If a supernova-born planet drifts close enough to a young star, it might get pulled into orbit, effectively becoming a planet in a new system. This would mean that some of the planets we see today might have had origins completely separate from their current host stars. The search for planets born from supernova remnants is still in its infancy, but if we find evidence that these worlds exist, it would revolutionize our understanding of planetary formation. It would prove that planets can emerge not only from the calm disks around young stars but also from the most violent and destructive events in the cosmos. And if these planets can survive and evolve over billions of years, it raises the tantalizing possibility that some of them might even support life. Could there be an ancient civilization living on a planet forged from the remnants of a dead star? Could life find a way to emerge in the extreme conditions of a supernova remnant? And if these planets are out there, drifting alone in the void, how many of them remain undiscovered, waiting for us to find them? The universe is full of secrets, and the idea that planets could form from supernova remnants might be one of the most extraordinary mysteries of all. The implications of planets forming from supernova remnants go beyond just rewriting what we know about planetary formation. If such planets exist, they could change our understanding of how planetary systems evolve, how elements are distributed throughout the galaxy, and even how life might arise in environments we previously thought were uninhabitable. But before we dive deeper into these possibilities, we need to address the biggest challenge to this idea. How would these planets actually form in such an extreme and chaotic environment? A supernova is one of the most violent events in the universe. When a massive star reaches the end of its life, it undergoes a catastrophic collapse, triggering an explosion that rips apart the star and sends its outer layers hurtling into space at speeds of thousands of kilometers per second. This explosion generates immense heat, producing temperatures that can exceed billions of degrees. The shockwaves from the explosion compress surrounding gas and dust, creating incredibly turbulent conditions. In this kind of environment, the process of planet formation as we know it seems nearly impossible. But let's break it down. If planets were to form from supernova remnants, the first step would be for the ejected material to slow down and cool enough for solid particles to begin condensing. This isn't as far-fetched as it sounds. After a supernova explodes, its remnants don't just vanish into nothingness. They expand outward and gradually mix with interstellar gas. Over time, some of this material begins to clump together, forming dense clouds rich in heavy elements. If conditions are just right, these clouds might become the starting point for planetary formation. One of the most interesting aspects of this idea is that planets formed from supernova remnants would have completely different chemical compositions from traditional planets. Most of the planets in our solar system formed from a protoplanetary disk that contained a mix of elements left over from previous generations of stars. This means that while they contain some heavier elements, they are mostly composed of lighter materials like silicates, carbon compounds, and hydrogen. A planet formed directly from supernova debris, however, would be made almost entirely of heavy elements: iron, nickel, gold, platinum, and other metals that are synthesized in the intense heat of the explosion. Imagine a planet with an iron-rich core so dense that its gravity is significantly stronger than Earth's. The surface of such a world might be covered in a crust of exotic metals, with mountains composed of elements rarely found in high concentrations on Earth. If the planet has enough mass to retain an atmosphere, it might contain gases we don't typically associate with planetary atmospheres, such as vaporized metals or unusual compounds formed in high radiation environments. Some of these planets might even be rich in radioactive elements, leading to extreme levels of internal heating that could drive volcanic activity unlike anything we've ever seen. But how would these planets take shape in the first place? One possibility is that after the supernova explosion, some of the debris forms dense clouds that collapse under their own gravity, creating structures similar to protoplanetary disks. Unlike traditional disks, however, these would be short-lived and chaotic, with material rapidly colliding and merging in a high-energy environment. If these disks last long enough for solid objects to form, they might give rise to planet-like bodies before dispersing completely. Another possibility is that rogue planets, already drifting through space, could act as seeds for the process. If a free-floating planet happens to pass through a supernova remnant at just the right time, it could sweep up debris and gain additional mass. Over time, the new material could accumulate on the planet's surface, changing its composition and potentially even altering its internal structure. This could explain some of the strange, metal-rich planets we've detected in the galaxy, worlds that don't quite fit the mold of traditional planetary formation theories. And then there's the question of what happens to these planets after they form. Do they remain as lonely wanderers in the void, or could they eventually become part of a new solar system? If a supernova-born planet is captured by a passing star, it might settle into an orbit and become a permanent part of that system. This would mean that some of the planets we see today might have origins we never expected. It's possible that some of the metal-rich exoplanets we've discovered were originally forged in supernova remnants before being captured by their current stars. There's even a chance that some of these planets could develop conditions suitable for life. While a planet drifting through space without a star might seem like a hopelessly frozen wasteland, internal heating from radioactive decay or tidal forces could provide enough warmth for liquid water to exist beneath the surface. If life can survive in the deep oceans of icy moons in our own solar system, such as Europa and Enceladus, then perhaps similar forms of life could exist on rogue planets formed from supernova remnants. This raises an even more fascinating question: could there be intelligent civilizations living on planets that were born from the remains of dead stars? If such civilizations exist, they would have evolved in an environment completely unlike anything we've ever known. They might not rely on sunlight at all, instead drawing energy from internal heat or chemical reactions. Their entire perception of the universe would be different from ours. Imagine a species that has never seen a sunrise, never experienced the changing of seasons, never known the concept of day and night. Would they even recognize stars as something important? Or would they view them as distant, irrelevant points of light in the sky? If such civilizations exist, they might be extraordinarily difficult to detect. Traditional methods of searching for extraterrestrial life rely on looking for planets in habitable zones around stars. But a supernova-born civilization would never have had a parent star to begin with. Their technology, their way of thinking, and even their understanding of the cosmos might be so different from ours that we wouldn't even know where to start looking for them. The possibility of planets forming from supernova remnants is one of the most mind-bending ideas in astrophysics, and it challenges nearly everything we think we know about planetary formation. If these planets exist, they could represent some of the strangest worlds in the universe, metal-rich giants, rogue wanderers, or even homes for life that evolved in complete darkness. And if they're out there, waiting to be discovered, then what else might be lurking in the vast, unexplored depths of space? The idea of planets forming from supernova remnants challenges the traditional view of planetary formation and forces us to rethink the very definition of what a planet is. If we consider planets as objects that form exclusively within the protoplanetary disks of young stars, then supernova-born planets would not fit that mold at all. Instead of slowly accreting material over millions of years in a stable disk, these planets might form rapidly in violent environments filled with turbulent gas, radiation, and debris moving at incredible speeds. This chaotic process could lead to planets that are vastly different from those found in typical solar systems. One of the biggest challenges in detecting such planets is that they would likely be rogue, drifting through space without a host star to illuminate them. Traditional exoplanet detection methods, such as the transit method, which relies on a planet passing in front of its star, or the radial velocity method, which detects the gravitational influence of a planet on its star, would be useless in these cases. Instead, astronomers would need to rely on other methods, such as gravitational microlensing, which can reveal the presence of rogue planets by observing how they bend the light of background stars. Microlensing events have already provided evidence of rogue planets floating through the galaxy, but so far, we have no way of determining where these planets came from. Some may have been ejected from their original solar systems due to gravitational interactions, but others could be remnants of past supernovae, wandering through space after forming in the debris fields of stellar explosions. If we could analyze the composition of these rogue planets, we might find clues that point to their origins. An unusually high concentration of heavy metals, for example, could indicate that they were formed directly from supernova remnants. Another possible way to detect these planets is by searching for residual heat. While most planets eventually cool over time, those formed from supernova material might contain an abundance of radioactive elements, which could keep them warm for billions of years. If such planets exist, they might emit faint infrared radiation, detectable by sensitive space telescopes designed to observe heat signatures in deep space. The presence of planets formed from supernova debris also raises intriguing questions about the role of supernovae in shaping the cosmos. We already know that supernovae play a crucial role in enriching the interstellar medium with heavy elements, which later become incorporated into new stars and planetary systems. But if supernova remnants can also directly form planets, then these explosions might be even more influential in the universe than we previously thought. Instead of simply being the endpoints of massive stars, supernovae could also be the birthplaces of entirely new worlds, worlds that exist independently of traditional star systems, and that may have properties unlike anything we've ever encountered. This could also change our understanding of galactic evolution. If planets can form in supernova remnants, then the overall number of planets in the universe might be far higher than we currently estimate. Right now, most planet formation models are based on the assumption that planets form exclusively in protoplanetary disks around young stars. But if planets can also emerge from the ashes of dead stars, then the total number of planetary bodies in the universe could be several times greater than previously believed. The implications for astrobiology are equally fascinating. We tend to think of life as something that emerges in stable, predictable environments, on planets orbiting stars in habitable zones, where conditions remain relatively constant for billions of years. But if planets can form in supernova remnants, then life may be far more adaptable than we assume. Some of the strangest forms of life in the universe might exist on these rogue planets, evolving under conditions of extreme radiation, high gravity, and unpredictable environmental changes. If such life exists, it would likely be vastly different from anything we know. Organisms on these planets might be adapted to survive without sunlight, relying instead on chemical energy sources like deep-sea hydrothermal vent life on Earth. Their biochemistry could be based on elements rarely found in large quantities on Earth, leading to entirely new biological structures and metabolic processes. If intelligent civilizations arose on these worlds, their entire understanding of the universe would be shaped by their unique environment. Imagine a civilization that has never seen a sky filled with stars because their world is a rogue planet drifting in interstellar space. They might not have a concept of time based on solar cycles, and their technological advancements could be entirely different from ours, developed in conditions that favor alternative forms of energy and communication. Would such a civilization even recognize us as intelligent beings if we made contact? Or would they perceive the universe in such a fundamentally different way that communication would be nearly impossible? These are the kinds of questions that make space exploration so exciting. The more we learn about the universe, the more we realize how little we actually know. If planets can form from supernova remnants, then the cosmic landscape is far more diverse than we ever imagined. It means that planetary formation is not limited to the quiet, stable environments of young solar systems, but can also occur in the most extreme and violent events in the universe. The search for these planets is just beginning, and future missions may provide more clues about their existence. Advanced telescopes like the James Webb Space Telescope and future infrared observatories could help detect the faint heat signatures of rogue planets formed in supernova remnants. Meanwhile, studies of exoplanets with unusual compositions could reveal whether any of them were forged in the remains of stellar explosions. If we do find these planets, it will be one of the most groundbreaking discoveries in astrophysics. It would redefine our understanding of how planets form, expand our view of the possible environments where life might exist, and challenge us to rethink the very nature of planetary systems. It might also give us a deeper appreciation for the universe's ability to create and destroy, showing us that even in death, stars can give rise to something new, a legacy written in planets, drifting silently through the cosmos, waiting to be found. The implications of planets forming from supernova remnants go beyond just the mechanics of planetary formation. They touch on the fundamental nature of matter in the universe, the processes that distribute elements across space, and the potential for habitable worlds in places we never expected. If such planets exist, they might not just be occasional anomalies. They could be an entirely new class of planetary objects, waiting to be classified and understood. To fully grasp the significance of this idea, we need to break down what happens in a supernova. When a massive star reaches the end of its life, it undergoes a catastrophic explosion that blasts its outer layers into space. This explosion spreads heavy elements, carbon, oxygen, silicon, iron, and even rarer elements like gold and uranium, into the surrounding interstellar medium. The core of the star may collapse into a neutron star or a black hole, but the rest of its material is hurled outward, sometimes at speeds exceeding 10,000 kilometers per second. For a long time, scientists believed that this ejected material simply mixed into space, eventually becoming part of new nebulae that would later collapse into new stars and solar systems. But what if, under the right conditions, some of this material could clump together almost immediately, forming new planetary bodies? Instead of waiting for millions of years to be recycled into the next generation of stars and planets, could these elements instead create something entirely different, worlds born in the chaotic aftermath of a stellar death? Theoretically, the intense shock waves and high-energy environment of a supernova explosion could trigger rapid accretion of dust and debris. If enough material sticks together quickly, it could form small planetary cores. These cores might then gather more matter through gravitational attraction, growing into fully formed planets in a process that happens far more quickly than conventional planetary formation. One of the most intriguing aspects of this idea is that these planets might be incredibly diverse in their composition. Unlike traditional planets, which form from a protoplanetary disk with a relatively uniform mixture of elements, supernova-formed planets would be made of whatever was left behind by the dying star. If the star was rich in carbon, the planet might be a carbon world, with graphite mountains and diamond layers beneath the surface. If it was rich in metals, the planet might be composed mostly of iron, nickel, and other heavy elements, making it far denser than Earth-like planets. There's also the question of atmosphere. Traditional planets develop their atmospheres from outgassing, volcanic activity releasing gases trapped inside the planet's interior, or from capturing gas from their surrounding environment. But a planet forming from supernova remnants would have no stable disk of gas to draw from. Instead, it might inherit whatever gases were expelled in the explosion. If a supernova-formed planet retained a thick envelope of volatile elements, it could have an atmosphere unlike anything we see in our solar system, possibly composed of exotic gases in unusual proportions. The radiation environment of a supernova explosion would also play a crucial role in shaping the properties of these planets. Any forming body would be subjected to extreme levels of radiation, stripping away lighter elements and possibly leaving behind only the densest materials. This could explain why some rogue planets drifting through space without a star, appear to be unusually massive and metallic. They may be remnants of supernova formation, where only the most resilient materials survive the blast. Another interesting question is whether any of these planets could retain enough heat to sustain liquid water or other solvents necessary for life. In our solar system, heat comes primarily from two sources: the sun and internal radioactive decay. A rogue planet formed from a supernova would lack a sun, but it might still generate heat from radioactive elements left over from its parent star. If such a planet had enough radioactive isotopes, it could maintain internal heating for billions of years, potentially creating underground oceans or subsurface environments where life could persist. This raises the possibility that some rogue planets might not just be barren wastelands drifting through the galaxy. They could be home to hidden, thriving ecosystems. Life on such a world would have to adapt to complete darkness, relying on chemical energy sources instead of sunlight. It might resemble the deep-sea extremophiles found on Earth, which survive in hydrothermal vent systems at the bottom of the ocean. If these planets exist in large numbers, they could significantly change our estimates of how many potentially habitable worlds are out there. Most current models of planetary habitability assume that planets need to be within the habitable zone of a star. But if rogue planets formed from supernova remnants can sustain internal heat for billions of years, then habitable conditions might exist in places we've never considered. There's also the possibility that these planets, instead of remaining rogue, could eventually be captured by passing star systems. If a wandering supernova-formed planet drifts close enough to a young star, it could be pulled into orbit, becoming a part of an entirely new solar system. In this case, an alien civilization studying its own planetary system might find one planet that doesn't quite match the others, one with a different composition, a strange orbital path, or an atmosphere that suggests an origin outside the system. The search for these planets is only just beginning, but future space telescopes might provide the evidence we need. Infrared observations could detect the heat signatures of rogue planets, while spectroscopic analysis could reveal unusual compositions pointing to a supernova origin. If we ever find a planet with an atmosphere rich in rare heavy elements, it could be a clue that it formed from the remains of an exploded star. Perhaps the most exciting part of this idea is that it suggests the universe is even more dynamic and unpredictable than we ever imagined. We tend to think of supernovae as endings, dramatic explosions that mark the deaths of stars. But what if they are also beginnings? What if, in the chaos of a stellar explosion, the building blocks of new worlds come together in ways we never expected? If this is true, then every supernova we see in distant galaxies might not just be the death of a star, it might also be the birth of new, strange, and mysterious planets, waiting to be discovered. Some of them may wander the galaxy alone, relics of ancient explosions. Others might find new homes, captured by passing stars and becoming part of young planetary systems. And some might even harbor life, evolving in the darkness, hidden from our view. The universe is full of surprises, and the possibility that planets can emerge from the ashes of dead stars is one of the most fascinating ones yet. With each new discovery, we get closer to understanding the true complexity of planetary formation and the incredible ways in which nature finds opportunities for creation, even in the most violent and extreme events. The search for these planets continues, And as our technology advances, we may one day find solid proof that some worlds are not born in the gentle cradles of protoplanetary disks, but in the fiery aftermath of a cosmic explosion. If supernova-formed planets do exist, they may be some of the oldest planets in the universe. Traditional planet formation relies on the slow accumulation of matter around young stars, a process that takes millions of years. But in the wake of a supernova, the conditions for rapid planet formation could be vastly different. The explosion disperses elements at incredible speeds, but if pockets of material experience just the right kind of turbulence, they could clump together almost instantly. Instead of taking millions of years, these planets might form within a few thousand years, or even faster. This leads to a fascinating possibility. Some of the first planets in the universe might not have formed around stars at all. Instead, they could have emerged from the explosions of the very first massive stars, before conventional planetary systems had even begun to take shape. If such planets exist, they could be relics from a time when the universe was barely a fraction of its current age, drifting silently through the cosmos, carrying the chemical signatures of some of the first stars that ever lived. Finding one of these planets would be like holding a piece of the early universe in our hands. It could tell us what the very first generations of stars were like, what elements they produced, and how matter behaved in the extreme environments of their deaths. If we could analyze the composition of a supernova-born planet, we might find traces of elements that no longer exist in high abundance anywhere else, short-lived isotopes or exotic forms of matter that were only present in the chaotic first few million years after the Big Bang. One of the biggest challenges in identifying these planets is that they wouldn't fit into any of our existing classifications. We have gas giants, terrestrial planets, ice worlds, and dwarf planets, but a planet forged from supernova debris might defy all of these categories. It could have an atmosphere made mostly of heavy metals instead of lighter elements like hydrogen and helium. It might have a density higher than anything we've ever observed in a planetary body, with layers of exotic material compressed by the shock of its formation. Its magnetic field, internal structure, and even surface chemistry might be unlike anything we've seen before. But how would we detect such a planet? Traditional exoplanet hunting methods rely on observing planets that orbit stars. The transit method, for example, detects planets by measuring the dip in a star's brightness as the planet passes in front of it. The radial velocity method looks for the gravitational wobble that a planet induces in its star. Both of these techniques assume that planets are orbiting stars, but a supernova-formed planet might not have a star at all. It could be completely rogue, floating alone in the vastness of space. This is where new observational techniques come into play. The James Webb Space Telescope, JWST, and future space observatories will be capable of detecting rogue planets through infrared imaging. Because planets retain heat for long periods, even a rogue planet formed billions of years ago could still emit a faint glow in the infrared spectrum. If we find an unusually dense, metal-rich object wandering through space, it could be a sign that we're looking at a supernova remnant planet. There's also the possibility of detecting these planets through their gravitational interactions. A rogue planet passing in front of a distant star could create a phenomenon called gravitational microlensing, temporarily magnifying the light from the background star. By carefully analyzing these lensing events, astronomers can determine the mass, size, and possible composition of the intervening planet. If we find a rogue planet with an unexpected composition, one that doesn't match any known planetary formation models, it could be evidence that it originated from a supernova explosion rather than a traditional protoplanetary disk. What's even more mind-blowing is that these planets might not just be wandering alone in the dark. Some of them could be part of hidden planetary systems orbiting dead stars, neutron stars, or black holes. If a supernova explosion leaves behind a neutron star instead of completely destroying the system, some of the debris might settle into a new orbit, forming a planetary system around the neutron star. These so-called pulsar planets have already been discovered, and their existence suggests that planetary formation can occur in environments far stranger than we ever imagined. In fact, the very first confirmed exoplanets ever discovered were found orbiting a pulsar, a rapidly rotating neutron star left over from a supernova explosion. These planets, known as PSR B1257 plus 12b, C, and D, were detected in the 1990s, and they remain some of the most unusual planets ever found. They exist in an environment bombarded by intense radiation and magnetic fields, yet they somehow formed and survived in the aftermath of a stellar explosion. If planets can form around pulsars, then the idea of planets forming directly from supernova remnants isn't so far-fetched after all. But what about life? Could a planet born from a supernova ever support life? At first glance, the answer might seem like a definite no. The conditions under which these planets form would be extreme: intense heat, high radiation, and violent shock waves. But over time, as the planet cools and stabilizes, it's possible that it could develop conditions suitable for life, especially if it retains an internal heat source. If a supernova-formed planet contains radioactive elements like uranium and thorium, it could generate enough internal heat to maintain subsurface oceans, similar to what we see on moons like Europa and Enceladus in our own solar system. Life on such a planet wouldn't rely on sunlight but on geothermal energy, just like deep-sea hydrothermal vent ecosystems on Earth. These alien biospheres could exist entirely underground, shielded from the harsh environment of space by thick layers of rock and metal. If we ever discover such a world, it would change our entire understanding of what makes a planet habitable. It would mean that life doesn't necessarily need a stable star or a well-defined habitable zone. It could arise in the most unexpected places, even on a planet forged in the violent death throes of a star. This idea also has implications for the search for extraterrestrial intelligence. If rogue planets formed from supernova remnants can support life, then intelligent civilizations might evolve in complete isolation, drifting through the galaxy without any connection to a home star. Such civilizations would face enormous challenges: no sunlight, no predictable day-night cycle, and limited energy resources. But if they managed to overcome these obstacles, they might develop entirely different ways of understanding the universe. Instead of measuring time based on the movement of a sun, they might rely on internal geological activity, or the occasional passing of distant stars. Instead of using radio signals to communicate, they might develop technologies that work in complete darkness, harnessing exotic forms of energy that we have yet to discover. The idea that planets can form from supernova remnants challenges everything we thought we knew about planetary formation. It suggests that the universe is far more creative than we ever imagined, finding ways to build new worlds even in the most destructive events. If we ever find solid evidence of one of these planets, it will open up a whole new chapter in our understanding of how planets form, what they're made of, and where life might exist in the cosmos. As our technology improves and our ability to detect rogue planets expands, we may one day find the smoking gun that proves these worlds exist. And when that happens, we'll have to rewrite the textbooks once again, acknowledging that sometimes, even in destruction, the universe finds a way to create something new. A rogue planet born from a supernova would be exposed to some of the most extreme conditions imaginable. In its early years, it would be bathed in the radiation left over from the supernova explosion, with high-energy particles bombarding its surface. Any atmosphere it started with might be blown away entirely, leaving behind only a dense, metallic core surrounded by whatever heavier gases could resist being stripped. Unlike Earth, where our atmosphere is held in place by the gentle pull of gravity and protected by a magnetic field, this kind of planet would need an incredibly strong gravitational grip to hold onto any gas at all. But what if it managed to keep an atmosphere? If the planet had enough mass, say, comparable to a super-Earth or even a mini-Neptune, it could retain a thick, high-pressure atmosphere that would act as an insulating blanket. This could keep its surface warm, even without a nearby star. The pressure could be so high that exotic forms of matter might exist on its surface, like superfluid oceans of metallic hydrogen or clouds of vaporized heavy metals. The chemistry of such an atmosphere would likely be unlike anything we've ever encountered, potentially rich in carbon, nitrogen, and even unexpected elements forged in the original explosion. If these planets formed close to a newly created neutron star, they might even interact with its magnetic field in strange ways. Neutron stars have some of the most powerful magnetic fields in the universe, and a planet in their vicinity could experience electromagnetic storms more intense than anything we've ever seen. Plasma arcs and radiation bursts could alter the planet's atmosphere, potentially creating weird chemical compounds that don't exist anywhere else. Over billions of years, these planets would cool and settle into their final forms. If they were rogue, drifting through space, they would likely experience cosmic impacts at a much higher rate than planets safely orbiting stars. Without a solar system to shield them, they would be vulnerable to collisions with asteroids, comets, and even other rogue planets. Some might even get captured by passing stars, suddenly gaining a host star billions of years after their violent birth. If that happens, the heat from their new sun could melt their frozen atmospheres, reigniting geological activity and possibly even creating conditions where liquid water could form. This raises a fascinating question. Could a planet that formed from supernova remnants, after billions of years drifting alone in space, suddenly become habitable if it falls into orbit around a star? If such an event has happened somewhere in the universe, it might mean that life can emerge not just on planets formed in protoplanetary disks but also on ancient rogue worlds that only later find themselves in a stable environment. But let's take it even further. What if life didn't just emerge after the planet was captured? What if it somehow survived the entire journey through interstellar space? If a supernova-formed planet retained enough internal heat, it might have subsurface oceans insulated beneath thick ice layers. These oceans could provide a stable, life-friendly environment for billions of years, even as the planet wandered through the cold emptiness of space. We already see something similar in our own solar system. Moons like Europa and Enceladus have vast subsurface oceans that remain liquid due to internal heating from tidal forces and radioactive decay. If a rogue planet formed from supernova remnants had a similar internal heat source, it might never have needed a star to sustain liquid water. Life could develop in complete darkness, powered by hydrothermal vents or chemical reactions deep within the planet's crust. This possibility changes everything about how we think of habitable worlds. It suggests that life might not be tied to traditional star systems at all. There could be billions of rogue planets drifting through the galaxy, each one carrying its own hidden ecosystem, completely invisible to us. These worlds wouldn't emit light, making them nearly impossible to detect with traditional telescopes. But they might still be out there, waiting to be found. Detecting them would require new techniques, and astronomers are already working on some of the most promising ones. One of the best methods for finding rogue planets is gravitational microlensing. When a rogue planet passes in front of a distant star, its gravity bends and magnifies the light from the background star, temporarily making it appear brighter. By carefully measuring these events, astronomers can determine the planet's size, mass, and even some of its composition. So far, microlensing has already revealed the existence of rogue planets, but we haven't yet identified one that was definitively formed from supernova remnants. If we find one that has an unusually high metal content, far beyond what's expected for a normal planet, it could be the evidence we need. The discovery of such a planet would be groundbreaking, proving that planets can emerge from the ashes of dying stars and survive for billions of years, even in the cold darkness of interstellar space. As technology advances, future telescopes might be able to directly image these planets in infrared, detecting the faint heat they still emit. And if we're lucky, we might one day get an even closer look. If a rogue planet happened to pass through our solar system, it could give us a once-in-a-lifetime opportunity to study one up close. Just like Oumuamua, the mysterious interstellar object that passed through our solar system in 2017, a rogue planet could enter our neighborhood unexpectedly, offering us a chance to send probes and study it directly. Imagine what we could learn from such an encounter. We could analyze its composition, search for signs of geological activity, and even look for biosignatures, chemical clues that hint at the presence of life. If we found something truly alien, something that evolved independently in the depths of space, it would be the greatest scientific discovery in history. But until that day comes, we can only speculate. The idea of planets forming from supernova remnants is still just a hypothesis, but it's one that fits within everything we know about physics, chemistry, and planetary science. If such planets exist, they are out there right now, drifting silently through the void, waiting for us to find them. And when we do, it will change everything we thought we knew about the origins of planets, the nature of the cosmos, and perhaps even the possibilities for life beyond Earth. One of the most fascinating possibilities is the role of radioactive elements. Supernovae are responsible for creating some of the heaviest elements in the universe, including uranium and thorium. These elements generate heat through radioactive decay, which is why planets like Earth still have active geology billions of years after their formation. But a planet formed from supernova remnants might have an even higher concentration of these elements, meaning its internal heat could last far longer than Earth's. This could be the key to its survival. While most planets cool down and become geologically dead, a supernova-born planet could stay warm internally for billions of years, even if it's floating alone in space. Its core might remain molten, fueling volcanic activity, plate tectonics, and even deep-sea hydrothermal vents. This internal heat could prevent it from becoming a frozen wasteland, keeping subsurface oceans liquid and creating an environment where life could persist. The concept of a dark biosphere becomes relevant here. If life exists on a rogue planet formed from supernova remnants, it wouldn't rely on sunlight. Instead, it would need to draw energy from other sources, such as geothermal heat or chemical reactions. Similar life forms exist on Earth in the deep ocean, where sunlight never reaches. These extremophiles thrive in high-pressure environments around hydrothermal vents, feeding on chemicals like hydrogen sulfide. On a rogue planet, similar organisms could evolve to harness the energy from geothermal activity. They might use chemosynthesis instead of photosynthesis, producing energy without any need for light. Over millions of years, more complex ecosystems could develop, with entire food chains built around chemical energy rather than solar energy. If such a world ever became part of a planetary system again, its life forms might have to adapt to sudden exposure to starlight, a process that could lead to evolutionary changes unlike anything we've ever seen. But what if these planets never get captured? What if they remain eternal wanderers, drifting endlessly through the cosmos? If so, they could accumulate an incredible history, traveling across the galaxy and experiencing conditions that no other planet has. They might pass through nebulae, collecting dust and chemicals that slowly alter their composition. They could encounter rogue asteroids, comets, or even other planets, leading to violent collisions that reshape their surfaces. There's also the question of planetary atmospheres. Even if a planet retains an atmosphere after a supernova explosion, how does it evolve over billions of years? Without a star, there's no solar wind to gradually strip it away, but there's also no steady source of heat to maintain stable conditions. Instead, the atmosphere could freeze and collapse onto the surface, only to be released again when internal heating causes periodic outgassing events. This cycle could create bursts of temporary habitability, where conditions shift between frozen wastelands and brief periods of warmth and liquid water. A planet like this could have a climate unlike anything we've ever seen. Instead of steady seasons, it might experience sudden, dramatic shifts driven by internal heat pulses. One year, it could be entirely frozen, and the next, volcanic activity could release enough greenhouse gases to warm it up, creating short-lived lakes or even oceans before everything refreezes. These cycles could last for thousands or even millions of years, making the planet a constantly changing, unpredictable world. If any form of life existed on such a planet, it would have to be incredibly resilient. It would need to survive deep freezes, extreme radiation exposure, and the constant risk of atmospheric collapse. Some life forms on Earth can endure similar conditions. Tardigrades, for example, can survive in the vacuum of space, extreme heat, and freezing cold. Could life on a rogue planet be just as tough? And what if such a planet passed close to another star? The heat from the star could trigger a rapid transformation, melting ice, igniting chemical reactions, and potentially restarting biological processes that had been dormant for millions of years. A once frozen world could become temporarily habitable, allowing life to flourish for a short period before drifting back into the cold. This raises another intriguing possibility. What if some of the habitable planets we've discovered weren't always in their current orbits? What if they were once rogue planets, wandering through space until they were captured by a star? If so, their geological history might be far older than their current solar system suggests, holding secrets of an ancient past that predates their current position. To find evidence of such worlds, astronomers are looking for planets with unusual isotopic compositions, chemical fingerprints that suggest they formed under different conditions than their surrounding planets. If we ever find a planet whose isotopic signature doesn't match its stars, it could be evidence that it once drifted through space before being captured. But let's push even further. Could an advanced civilization ever exist on a rogue planet? At first glance, it seems impossible. Without a star, there's no solar energy to harness, and without a stable climate, agriculture would be nearly impossible. But what if such a civilization found ways to survive using geothermal energy? Imagine an underground world, where cities are built beneath the surface, using the planet's internal heat for warmth and power. Instead of relying on photosynthesis, these beings might cultivate fungi or chemosynthetic bacteria as their primary food source. Their entire civilization could be hidden beneath thick ice or rock, making them almost undetectable from space. If such a civilization existed, would they even know that stars and other planets existed? If they evolved underground, they might never have seen the sky. Their entire understanding of the universe could be limited to the deep caves and tunnels of their world, with no concept of an outside cosmos. But what if they eventually made their way to the surface? Imagine the moment when they first break through the ice and see the vastness of space for the first time. Would they realize they were drifting through the galaxy, completely alone? Would they try to find a new home, seeking out a star to orbit? Or would they simply continue their underground existence, unaware of the greater universe beyond? These questions stretch the limits of what we can imagine, but they highlight just how mysterious rogue planets truly are. If planets can form from supernova remnants, their stories could be unlike anything we've ever encountered. They might carry the scars of their explosive origins, retain atmospheres against all odds, and even host life in ways we've never considered. And if we ever detect one of these planets, it could revolutionize our understanding of planetary formation, habitability, and even the potential for life beyond Earth. For now, all we can do is search. Rogue planets are difficult to detect, but every year, we refine our techniques, bringing us closer to finding the first true example of a world born from a supernova. The day we discover one could be the day we rewrite the history of planetary science, proving that planets can emerge not just from the gentle process of accretion, but from the violent deaths of stars themselves. And who knows? Maybe one of these planets is out there, silently drifting through the cosmos, waiting for us to find it. Let's think about how we might actually find one of these planets. Detecting rogue planets is already a challenge, but finding one specifically formed from supernova remnants is even harder. Since they don't orbit a star, traditional methods like the transit method, where a planet passes in front of a star and blocks its light, won't work. We also can't rely on the radial velocity method, which detects the wobble of a star due to a planet's gravity. Instead, astronomers have to use more indirect methods, like gravitational microlensing. This technique relies on the way massive objects bend and magnify the light of background stars due to gravity. If a rogue planet passes in front of a distant star, it can briefly magnify the star's light, allowing us to estimate its size and mass. While this method has led to the discovery of several rogue planets, identifying whether they specifically formed from supernova remnants is another challenge entirely. One way we might be able to tell is by looking at their chemical composition. If a planet formed from the debris of a supernova, its elemental makeup should be different from planets that formed through normal accretion. For example, it might have an unusually high concentration of heavy elements like iron, nickel, and even radioactive isotopes. These elements are common in supernova ejecta, and if they're present in unusually high amounts, they could provide a clue about the planet's origins. Spectroscopy could help us analyze these compositions. Even though rogue planets don't have a nearby star illuminating them, they still emit some infrared radiation due to residual heat. If we could capture this light and break it down into its individual wavelengths, we could look for signatures of elements that hint at a supernova origin. But there's another fascinating possibility. What if these planets still retain traces of their original supernova explosion? When a star goes supernova, it releases a shockwave that can embed elements deep into the forming planetary material. If we could find evidence of these shockwave-induced changes, perhaps in the form of unusual mineral structures or isotopic ratios, we might be able to confirm that a planet was born from stellar death. There's also the question of whether a supernova-born planet could retain a magnetic field. Earth's magnetic field is crucial for protecting us from cosmic radiation, and it's generated by the motion of molten iron in our planet's core. If a rogue planet formed with a highly metallic core, enriched by supernova debris, it might generate an even stronger magnetic field than Earth's. This could be crucial for retaining an atmosphere and shielding the surface from harmful radiation. Speaking of atmospheres, could a planet formed from a supernova actually hold onto one? At first glance, it seems unlikely. The sheer force of a supernova explosion would strip away any gases, leaving the planet exposed to the vacuum of space. But over time, volcanic activity could release new gases from the interior, slowly building up an atmosphere. If the planet had enough mass, its gravity could hold onto these gases, creating conditions that might support life. Even more interesting is the possibility that these planets could have exotic atmospheres unlike anything we see in our solar system. The high concentration of heavy elements might lead to the formation of unusual compounds, creating thick, metallic clouds or strange chemical reactions in the air. If we ever discover one of these planets, its atmosphere could be unlike anything we've ever seen before. But what if these planets aren't just floating through space forever? Could they ever find a new home around a star? It turns out that rogue planets can, in rare cases, be captured by a passing star's gravity. If a rogue planet drifts too close to a star, it might enter a stable orbit and become part of a new planetary system. This means that some of the planets we see today may have originally been born from supernova remnants before being captured by a different star billions of years later. If that's the case, some of the exoplanets we've discovered might have a much older and more violent history than we realize. They could have spent millions of years drifting through space before finally settling into an orbit around a new star. If we find an exoplanet with an unusually high concentration of heavy elements, it might be evidence that it was once a rogue planet born from a supernova. Imagine if one of these planets ended up in a habitable zone, a region where temperatures allow liquid water to exist. It could have spent billions of years as a frozen wasteland before suddenly finding itself in the perfect environment for life to emerge. What if that's already happened somewhere in the galaxy? What if there's a planet out there that was once a rogue world, only to be captured by a star and transformed into a life-bearing world? And what if we find one close to home? If rogue planets exist in large numbers, there could be one lurking in the outer reaches of our own solar system, hidden in the darkness beyond Pluto. Some scientists have speculated that a yet undiscovered planet, sometimes called Planet 9, could be orbiting far beyond Neptune. If it exists, could it be a former rogue planet that was captured by our Sun? If so, studying it could give us the first real evidence of a planet formed from supernova remnants. It could be the missing link that proves these worlds exist, showing us that planets don't just form in the calm disks around stars, but also in the chaos of stellar death. And that brings us back to the bigger question: if planets can form from supernova remnants, how many of them are out there? Could they be one of the most common types of planets in the universe? The more we learn about exoplanets, the more we realize that planetary formation is far more complex than we once thought. We used to believe that all planets formed in stable disks around young stars, but we now know that planets can be born in extreme environments, around pulsars, in binary systems, and possibly even from supernova remnants. If we ever find definitive proof of such a planet, it would change our understanding of how planets form and evolve. It would show us that planets can arise not just from the gentle process of dust accretion, but also from the violent deaths of stars. It would mean that planetary formation is not just a story of creation, but also of destruction and rebirth. And who knows? Maybe one of these planets is out there right now, drifting silently through the void, carrying the elements of a dead star, waiting for us to find it. Let's consider what it would take to actually confirm the existence of a planet formed from supernova remnants. While theories and indirect evidence are intriguing, solid proof is what would truly change our understanding of planetary formation. So, how could we find such a planet and be certain of its origin? One of the most promising methods would involve detecting specific isotopic ratios that are unique to supernova nucleosynthesis. When a star explodes, it creates heavy elements through nuclear fusion and neutron capture, resulting in isotopes that don't form naturally in most planetary systems. If we could analyze a rogue planet's composition and find an abundance of these isotopes, like certain forms of iron, nickel, or even rare elements like technetium, which has no stable isotopes, it would be strong evidence that the planet originated from a supernova explosion. The challenge is that detecting these isotopes isn't easy. On Earth, we can study isotopes by analyzing rock samples directly, but for a rogue planet drifting through interstellar space, that's not an option. Instead, we would need to use advanced spectroscopy, possibly with next-generation telescopes like the James Webb Space Telescope or future observatories designed for exoplanet research. By studying how the planet emits or absorbs light, we could infer its chemical composition and look for the telltale signs of a supernova origin. But there's another way we might find these planets, looking at young supernova remnants themselves. When a star explodes, its debris doesn't just scatter randomly. It can sometimes form dense clumps and structures within the expanding cloud. If we observe a supernova remnant at the right stage of evolution, we might find hints of planet-sized objects forming within the debris field. These objects could be early-stage planetary cores, slowly accumulating material as they travel through space. Some astronomers have suggested that pulsars, rapidly spinning neutron stars left behind after supernovae, might help us in this search. We already know that planets can exist around pulsars, as seen with the first exoplanets ever discovered orbiting Pulsar B1257+12. If a supernova-born planet remains gravitationally bound to a pulsar, it could give us direct access to a world that formed from stellar death. By studying these systems closely, we might find the first undeniable proof of a planet formed from supernova remnants. And what if we could go even further? What if, someday, we could send a probe to one of these planets and analyze its surface directly? Imagine landing on a world that was once part of a massive star, now floating alone in the void. Its surface might be covered in exotic minerals, its crust infused with elements forged in the final moments of a dying star. It could be one of the most unique planets in the universe, a world shaped by the chaos of stellar destruction, yet still capable of holding on to its own identity. There's even the possibility that such a planet could be a relic of ancient cosmic history. If planets can form from supernova remnants, then some of them might have originated billions of years ago, in the early universe when massive stars were far more common. These planets could be some of the oldest objects in existence, surviving across cosmic time as remnants of a bygone era. So what does all of this mean for our understanding of planetary formation? It suggests that the process is far more diverse than we ever imagined. Planets don't just form in quiet, stable conditions, they can also emerge from the aftermath of violent stellar deaths. If we confirm the existence of these planets, it would redefine what we consider a normal planet, expanding our understanding of how worlds come into being. And that raises another fascinating question: could life exist on one of these planets? At first, it seems unlikely. A world formed from supernova debris would start off as a harsh and inhospitable place, bombarded by radiation and stripped of any atmosphere. But over time, as it cools and stabilizes, could it develop conditions that support life? If the planet retained enough heat from its formation, it might sustain subsurface oceans, similar to what we see on moons like Europa or Enceladus. Even in the darkness of interstellar space, hydrothermal vents could provide the necessary energy for life to exist. If microbial life can survive in extreme environments on Earth, like deep-sea vents, radioactive waste sites, and frozen Antarctic lakes, then perhaps it could also emerge on a planet formed from supernova remnants. And if life did develop on such a planet, it would have to adapt to an entirely different set of conditions than anything we know. Without sunlight, it might rely on chemosynthesis instead of photosynthesis, deriving energy from chemical reactions rather than light. It might evolve unique biological structures to withstand radiation, extreme temperatures, and a lack of a stable atmosphere. If we ever found life on such a planet, it would be unlike anything we've ever seen. But there's an even wilder possibility. What if intelligent life arose on a planet like this? If a civilization evolved on a rogue planet that formed from supernova remnants, it would grow up in a world utterly unlike our own. It would never see a sun rise or set, never experience seasons, and never have a day-night cycle. How would that shape its understanding of the universe? Would it even conceive of stars as distant objects, or would it see them only as tiny points of light in the void? And if such a civilization existed, how would it develop technology? Without a nearby star, traditional solar power wouldn't be an option. Would they rely on geothermal energy, tapping into the heat of their planet's interior? Or perhaps they would harness radioactive decay, using the very elements left behind by the supernova to generate power? If intelligent life did evolve on one of these planets, it would likely have a completely different perspective on the universe than we do. While we see ourselves as creatures of a stable, sunlit world, they would see themselves as survivors of chaos, born from destruction and adapted to darkness. If they ever looked out into space and saw planets orbiting stars, they might find those worlds as strange and unfamiliar as we find the idea of rogue planets. And that raises a final, mind-bending thought. What if we've already encountered such a civilization? If a species evolved on a rogue planet, it might develop a way to travel through space, searching for energy sources or new environments to inhabit. If they ever found their way to a solar system like ours, would we recognize them as intelligent beings? Or would they be so different from anything we expect that we wouldn't even realize what we were looking at? The more we think about planets forming from supernova remnants, the more questions arise. It challenges everything we assume about how planets are born, how they evolve, and what kinds of environments might be capable of sustaining life. If we ever find one of these planets, it won't just be another discovery, it will be a revelation, forcing us to rethink what we know about the cosmos. And perhaps, somewhere out there, drifting silently through the void, there's a planet carrying the secrets of a dead star, waiting for us to find it. If a planet formed from supernova remnants truly exists, it would be one of the most extreme and fascinating objects in the universe. Imagine a world with a surface made of exotic heavy elements, infused with the radioactive remains of a once massive star. This planet would be nothing like Earth, Mars, or even the gas giants in our solar system. It would be a world born from chaos, surviving in the aftermath of destruction, possibly floating alone in the darkness of space as a rogue planet, or orbiting the remnants of the star that gave it life. One of the biggest challenges in finding such a planet is the sheer vastness of space. Rogue planets, in particular, are difficult to detect because they don't emit their own light and don't transit in front of stars like traditional exoplanets. However, advances in astronomical techniques are giving us new ways to search for them. One promising method is gravitational microlensing, which relies on the bending of light caused by massive objects. If a rogue planet formed from supernova remnants were to pass in front of a distant star, its gravity could temporarily magnify the star's light, revealing the presence of an unseen world. Another approach involves infrared telescopes, like the James Webb Space Telescope. While a supernova-born planet might not reflect much visible light, it could still emit a faint glow in the infrared spectrum due to residual heat from its formation or radioactive decay. If we could identify such a heat signature in an isolated object drifting through interstellar space, it could be a strong candidate for a planet formed from a supernova explosion. But what would such a planet actually look like? Would it be a barren wasteland, scarred by intense radiation, or could it be something more unexpected? If it had a thick enough atmosphere, it might be able to retain heat for millions of years, potentially creating conditions where exotic chemistry could take place. While life as we know it might struggle to survive, strange chemical reactions could give rise to new, unknown forms of complexity. And then there's the question of stability. If a planet forms from supernova debris, how long could it last? Would it eventually break apart due to radiation and extreme temperatures, or could it persist for billions of years, just like traditional planets? Some scientists speculate that these worlds might be relatively short-lived, existing only for a few million years before being destroyed by gravitational interactions or collisions with other interstellar objects. Others believe that if a planet formed from a supernova manages to cool and stabilize, it could survive indefinitely, drifting through the cosmos as a relic of stellar death. One of the most intriguing aspects of this idea is that it challenges our traditional models of planetary formation. The classic theory suggests that planets form from protoplanetary disks around young stars, gradually accumulating matter over millions of years. But if planets can also form from the wreckage of exploded stars, it means the universe has more than one way to create worlds. It suggests that planets might be far more common than we ever imagined, forming not just in the peaceful environments of young star systems, but also in the violent aftermath of stellar destruction. And if planets can form this way, what else could be out there? Could there be entire planetary systems that originated from supernova remnants, with multiple worlds orbiting a neutron star or a black hole? Could there be planets with surfaces rich in elements that are incredibly rare on Earth, like gold, platinum, or uranium? If a planet formed from supernova remnants, it might contain higher concentrations of these heavy elements than any other world we've discovered. In fact, if we could one day reach such a planet, it might be one of the most resource-rich objects in the universe. Thinking even further ahead, what if humanity could one day harness the energy of such a world? A planet rich in heavy elements and radioactive isotopes could provide an almost limitless supply of energy, potentially fueling space exploration and colonization efforts. If we ever reach a point where we can travel between the stars, finding and exploiting planets formed from supernova remnants might become a crucial part of our survival. But perhaps the most mind-bending idea is that these planets could act as natural laboratories for studying the universe's most extreme conditions. By analyzing their compositions, temperatures, and radiation levels, we might learn more about the physics of supernovae, the formation of heavy elements, and even the origins of the universe itself. These worlds could hold clues about the first stars that ever existed, the formation of black holes, and the ways in which galaxies evolve over billions of years. So the question remains, do these planets actually exist? Right now, we don't have direct proof. But with each new discovery in exoplanet research, we move closer to answering that question. If a planet formed from supernova remnants is out there, it's only a matter of time before we find it. And when we do, it will change everything we thought we knew about how planets are born and what kinds of worlds can exist in the universe. Until then, we can only wonder what such a planet might be like. Somewhere, drifting through the darkness of interstellar space, there could be a world unlike any other, a planet forged in fire, shaped by destruction, and waiting for us to uncover its secrets. If such a planet exists, it would defy nearly every conventional rule of planetary formation. Traditional planets form within the swirling disks of gas and dust that surround young stars, slowly accumulating matter over millions of years. But a planet emerging from supernova remnants would be born in chaos, forming rapidly from scattered debris in a turbulent and violent environment. It wouldn't have the luxury of a stable, nurturing protoplanetary disk. Instead, it would be piecing itself together in the middle of an explosion's aftermath, surrounded by radiation, extreme heat, and expanding shockwaves of gas and energy. What kind of elements would dominate this kind of world? Unlike Earth, which formed from a mixture of common rocky materials like silicon and iron, a planet born from a supernova could have a far more exotic composition. Supernovae create heavy elements, including uranium, thorium, gold, platinum, and even rare isotopes that barely exist on Earth. This means that if such a planet formed and solidified, it could be incredibly dense, rich in rare metals, and potentially even more geologically active than Earth due to the radioactive decay of these heavy elements. But how would this planet even form? The biggest challenge is the fact that a supernova explosion doesn't leave behind a slow-moving cloud of gas and dust like a typical stellar nursery. Instead, it sends debris flying outward at extreme velocities, sometimes at a significant fraction of the speed of light. For a planet to emerge from this chaos, there would have to be some mechanism that slows the material down, allowing it to clump together and form a stable mass. Some scientists speculate that the presence of a nearby surviving star, or the remnants of the original star itself, could provide enough gravitational influence to hold the material together long enough for planetary formation to occur. There's also the question of location. If a planet formed from supernova remnants, would it stay within the star system where the explosion happened, or would it be flung out into interstellar space? Many supernovae are powerful enough to disrupt their entire star system, sending any surviving planets careening into the void as rogue planets. If a new planet managed to form in the aftermath, it too might be ejected, doomed to drift through space with no sun to warm it. This would make such planets incredibly difficult to find, but not impossible. Astronomers are already detecting rogue planets, free-floating worlds that exist between the stars. Some of these planets are thought to have formed normally and were later ejected from their star systems due to gravitational interactions. But if even a fraction of rogue planets were formed from supernova debris, it would mean that the process is not just possible, but potentially common. The more we study rogue planets, the closer we may get to finding definitive proof that planets can form in the wake of stellar destruction. But what would it be like to stand on such a planet? Assuming it had a solid surface, the conditions would likely be extreme. Without a nearby star, the planet would be in perpetual darkness, with surface temperatures plunging to near absolute zero unless there was some internal heat source. If radioactive elements were abundant, the planet could still have an active geology, with volcanoes, geysers, and even subsurface oceans heated by radioactive decay. This opens up another possibility. Could such a world support life? Life as we know it depends on liquid water, stable temperatures, and a source of energy. While a supernova-born planet wouldn't have a sun, it might still have geothermal heat, which could sustain life deep beneath the surface. Some of the most extreme life forms on Earth, like bacteria that thrive in deep-sea hydrothermal vents, rely on chemical energy rather than sunlight. If similar life forms could evolve on a supernova-born planet, it would prove that life can emerge in some of the most hostile environments imaginable. But even if these planets don't host life, they could still be valuable in ways we can't yet predict. Imagine a future where humanity explores the galaxy and stumbles upon a planet formed from a supernova. Its crust might be rich in rare metals, its interior a treasure trove of elements we struggle to obtain on Earth. Mining such a world could provide the materials needed for deep space exploration, artificial habitats, or even advanced energy sources we haven't yet discovered. There's also the possibility that such planets could tell us something about the origins of our own solar system. If planets can form in the wake of a supernova, it raises the question, did our solar system emerge from the remnants of an ancient explosion? Some scientists believe that a nearby supernova may have played a role in shaping the early solar system, seeding it with heavy elements and influencing the formation of planets. If we find a planet formed from supernova debris elsewhere in the galaxy, studying it could help us understand how common such events are and whether our own world has a similar origin story. Ultimately, the search for planets formed from supernova remnants is a search for the extraordinary. If these planets exist, they challenge everything we thought we knew about how worlds come into being. They force us to rethink our models of planetary formation, to expand our ideas about what kinds of environments can create planets, and to consider the possibility that the universe is even stranger than we ever imagined. For now, the evidence remains elusive. We don't yet have a confirmed detection of a planet formed from supernova remnants, but every new technological advancement brings us closer to that discovery. The next generation of space telescopes, gravitational wave detectors, and deep space probes could provide the breakthrough we need. And when that moment comes, it will rewrite our understanding of planetary science, proving that even in the aftermath of destruction, new worlds can rise from the ashes. Somewhere out there, drifting through the cold void of space, there could be a planet that was born in fire, forged in the heart of an exploding star, and waiting for us to find it. The question is, how long will it take before we finally uncover its secrets? If planets can form from the remnants of a supernova, then the entire life cycle of a star would have a hidden second act. Traditionally, we think of supernovae as the explosive deaths of massive stars, violent, destructive events that mark the end of a star's existence. But what if, instead of being purely destructive, these explosions actually create something new? What if the scattered elements, flung across space at incredible speeds, eventually coalesce into new planets, carrying with them the remnants of the star that once was? The idea isn't as far-fetched as it might seem. We already know that supernovae play a crucial role in spreading heavy elements across the universe. Every atom of gold, platinum, uranium, and even many elements in our own bodies was forged in the heart of an exploding star. Without supernovae, the universe would be a far simpler place, composed mostly of hydrogen and helium. But if these heavy elements are scattered into space, can they ever come back together to form something solid, something like a planet? For a planet to emerge from supernova debris, several conditions would need to be met. First, the material ejected from the explosion must slow down. Supernovae expel matter at tremendous velocities, often thousands of kilometers per second. If the debris simply races off into interstellar space, it won't have a chance to form anything substantial. However, if the explosion occurs within a dense enough environment, like a molecular cloud or near another massive star's gravity, some of that material could be slowed down and captured. This brings up another possibility. What if a nearby star, perhaps a binary companion to the exploding star, gathers up the supernova remnants in its gravitational pull? We already know that binary systems are common in the universe. If one star in a binary pair goes supernova, the material it expels could end up forming a dense disk around the surviving star. This process isn't too different from how planets form around young stars in traditional protoplanetary disks. The difference here is that the material would be far richer in heavy elements, perhaps even containing elements that are rare in ordinary planetary systems. If a planet formed from such a disk, it could be unlike anything we've ever seen. Most planets, including Earth, are made primarily of lighter elements like oxygen, silicon, magnesium, and iron. But a planet that formed from supernova debris might have an entirely different makeup, with much higher concentrations of gold, platinum, or even exotic radioactive elements. This could lead to a world with extreme internal heating, driven by the decay of unstable isotopes, leading to intense volcanic activity and a constantly shifting surface. But what if the explosion didn't happen in a binary system? Could a planet form from a supernova's remnants all on its own? One potential scenario is that the debris ejected from the explosion eventually slows down enough to collapse under its own gravity. This would require the supernova material to remain dense enough and cool enough to clump together over time. While it's a challenging process, it's not impossible. In some cases, supernova remnants can create dense, compact clouds of gas and dust that could serve as the foundation for planetary formation. This raises another fascinating possibility: planets forming in completely unexpected locations. Most planets are found in orbit around stars, but what if a planet could form in deep space, far from any stellar system? If a planet were to coalesce from supernova debris in interstellar space, it would be a rogue planet from the moment of its birth, drifting alone in the darkness, carrying the atomic remains of the star that once gave it life. If such a planet existed, it would be nearly impossible to detect. Rogue planets are already difficult to find since they don't emit their own light and don't transit in front of a host star. A planet formed from supernova remnants could be even more elusive, given its unusual composition and potentially small size. However, future advancements in infrared astronomy, gravitational microlensing, and deep space probes might give us a way to detect these objects. Some astronomers have even suggested that the strange chemical signatures seen in certain interstellar objects, such as Oumuamua, the first known interstellar visitor detected passing through our solar system, could hint at the existence of planets or planetary fragments formed from unusual processes, including supernovae. While there's no direct evidence yet, it's an exciting idea that challenges our understanding of planetary formation. The implications of planets forming from supernova remnants go beyond just astronomy. If these planets exist, they could contain unique clues about the history of the universe, preserving isotopes and elements that aren't typically found in traditional planetary systems. They might also help answer one of the biggest questions in science: where do the building blocks of life come from? We already know that supernovae are responsible for seeding the universe with many of the elements essential for life. But if planets can form directly from supernova debris, it raises the possibility that life itself, or at least its essential ingredients, could emerge from these worlds. A planet born from a supernova could have an entirely different chemistry from Earth, with unique energy sources and geological processes. If extremophiles on Earth can thrive in radioactive environments and deep-sea vents, could life evolve on a world forged from an explosion? It's a question we may not be able to answer anytime soon, but every new discovery brings us closer. The more we learn about rogue planets, the more we refine our search for the unexpected. And one day, we might just find the first evidence of a world born not in the gentle warmth of a protoplanetary disk, but in the violent aftermath of a dying star. It's fascinating to think about what such a planet would actually look like. If a world formed entirely from supernova remnants, it would likely be rich in heavy elements, giving it a geological structure unlike anything we've ever seen. Traditional rocky planets like Earth are composed mostly of silicate minerals, with a core of iron and nickel. But a planet born from supernova debris could have an unusual chemical composition, potentially with high concentrations of rare metals and radioactive elements. This could make the planet's internal structure vastly different from anything we're familiar with. For example, if the planet contained significant amounts of uranium or thorium, its core could generate immense amounts of heat through radioactive decay. This could lead to extreme volcanic activity, with constant eruptions and a constantly shifting surface. Unlike Earth, where volcanic activity is driven largely by residual heat from planetary formation and tidal interactions, a supernova-formed planet might have a much more intense and prolonged heat source, keeping it geologically active for billions of years. The presence of exotic elements could also affect the planet's atmosphere, if it has one at all. Depending on how the material coalesced, the planet could end up with an incredibly dense atmosphere composed of unusual gases, potentially even elements that would be rare on a normal rocky planet. If the planet formed in isolation, drifting through interstellar space, it might retain a thick atmosphere of hydrogen and helium, similar to gas giants, since there would be no stellar wind to strip these lighter elements away. But what if the planet formed in orbit around another star? This opens up an entirely different set of possibilities. If a planet made from supernova remnants ended up within the habitable zone of a new star, it might develop liquid water on its surface. This would be a completely new type of exoplanet, one formed from the ashes of a dead star but reborn in the orbit of a younger one. If such a world exists, it could be one of the most extreme places in the universe, with a surface littered with heavy metals and an atmosphere filled with unusual gases. There's also the possibility that these planets could be incredibly dense. Since supernova remnants are rich in heavy elements, a planet formed from them might have an exceptionally high mass for its size. This could lead to extreme gravity, making it a harsh environment for any form of life. Imagine a world where gravity is 2 or 3 times stronger than Earth's, crushing anything that tries to move on its surface. The temperature of such a planet would depend on many factors, including whether it has an atmosphere, how much heat it retains, and whether it orbits a star. If it formed as a rogue planet, it could be an ice-covered world, with a thick layer of frozen material insulating a potentially warm core. Some astronomers believe that rogue planets with internal heating could have subsurface oceans, similar to moons like Europa and Enceladus. If a supernova-born planet had enough internal heat, it might sustain liquid water beneath its surface, raising even more questions about its potential habitability. One of the biggest challenges in studying these hypothetical worlds is detecting them in the first place. Since most planetary detection methods rely on a planet passing in front of a star or gravitationally affecting a star's motion, rogue planets are incredibly difficult to find. However, advancements in infrared astronomy and gravitational microlensing techniques have allowed scientists to detect free-floating planets in deep space. If we ever discover a planet with an unusually high concentration of heavy elements, it could be a strong candidate for a world formed from supernova remnants. There's even a possibility that we've already encountered material from such a planet without realizing it. Some interstellar objects, like Oumuamua, have shown unusual chemical signatures that don't match typical asteroids or comets. If fragments of a supernova-born planet were ejected into space, they might travel through the galaxy for millions of years before eventually passing through our solar system. Studying these objects could provide a glimpse into the unique chemistry of these planets. The idea of planets forming from supernova remnants challenges our understanding of planetary formation and forces us to rethink what's possible. If these planets exist, they could provide insights into the life cycle of elements, the role of supernovae in shaping the cosmos, and even the origins of life itself. After all, if life can develop on Earth, which was formed from older stellar material, could it also arise on a planet made entirely from the remains of an exploded star? The universe is full of surprises, and as our technology improves, we may one day confirm the existence of these extraordinary worlds. Until then, we can only imagine what it would be like to stand on the surface of a planet born from a supernova, surrounded by a landscape rich in the elements of destruction and creation. If such a planet existed, it wouldn't just be a scientific curiosity, it would be a treasure trove of materials that are incredibly rare on Earth. Supernovae forge some of the heaviest elements in the universe, including gold, platinum, and uranium. A planet formed from supernova remnants might be covered in these valuable materials, making it an unimaginably rich world in terms of raw resources. This raises an intriguing possibility. Could a supernova-born planet one day become a target for interstellar mining? While it's purely speculative at this point, humanity's interest in space mining is already growing. Companies and space agencies are exploring the potential of extracting resources from asteroids, the Moon, and even Mars. If a planet composed of supernova debris were discovered, its immense concentration of heavy elements could make it one of the most valuable places in the cosmos. However, mining such a world would come with extreme challenges. First, there's the issue of gravity. If the planet is significantly denser than Earth due to its heavy element composition, working on its surface might be nearly impossible. Imagine trying to walk on a world where the gravity is 3 or 4 times stronger than Earth's. It would feel like carrying a crushing weight at all times. Any mining operation would require advanced technology, possibly robotic systems designed to withstand the intense gravitational pull. Then there's the possibility of extreme radiation. If the planet contains high levels of radioactive elements like uranium or thorium, its surface could be dangerously radioactive. In fact, some areas might be completely inhospitable due to the sheer amount of radiation emitted by decaying isotopes. This could mean that any potential mining efforts would have to be done remotely, with advanced shielding and automation. Another challenge is simply reaching such a planet. If it exists as a rogue world drifting through interstellar space, it could be thousands of light years away from the nearest inhabited system. Even if humanity one day achieves interstellar travel, locating and reaching a supernova-born planet would be a monumental task. However, if such a planet orbits a nearby star, it might become one of the most studied objects in astronomy. But beyond its material wealth, such a planet could also hold answers to some of the biggest questions in science. Could life exist on a world formed from supernova remnants? While it might seem unlikely, the possibility can't be dismissed entirely. If the planet retained enough heat, had a protective atmosphere, and developed the right chemical conditions, life might be able to emerge in ways we can't yet comprehend. One fascinating possibility is that life on a supernova-born planet might be fundamentally different from anything we know. On Earth, life is based on carbon chemistry, but extreme environments can lead to alternative biochemistries. If a planet were rich in exotic elements, could it host life forms that use different building blocks? Some scientists have speculated about the possibility of silicon-based life, as silicon shares chemical similarities with carbon. If such life exists anywhere, a supernova-born planet could be an ideal place to look. Even if life never develops on these planets naturally, they could still serve as stepping stones for interstellar colonization. If future civilizations can locate and harness the resources of a supernova-born planet, they might use it as a base for further expansion. A planet rich in rare metals and heavy elements could become a hub for advanced technology, providing materials essential for building interstellar spacecraft, fusion reactors, and other high-energy systems. Interestingly, there's another way these planets could impact the future of space exploration, by acting as natural laboratories for studying extreme physics. If a planet formed from supernova debris contains unique isotopes or materials that don't exist in large quantities elsewhere, studying them could lead to breakthroughs in nuclear physics, materials science, and even our understanding of fundamental forces. For instance, if the planet contains high concentrations of superheavy elements, those beyond what we see on Earth, it could provide insights into the so-called island of stability. Some theoretical elements, predicted to exist at extremely high atomic numbers, could have unusual properties, such as extreme resistance to radiation or superconductivity at high temperatures. If a supernova-born planet contains these elements in naturally occurring deposits, it could revolutionize multiple fields of science. The search for such planets is still in its infancy, but new telescopes and space missions could one day provide direct evidence. Instruments like the James Webb Space Telescope, as well as future observatories, might detect exoplanets with chemical signatures indicative of a supernova origin. Looking for worlds with an unusually high abundance of heavy elements could be the first step in confirming their existence. In the distant future, if humanity ever does travel between the stars, these planets could become some of the most strategically important locations in the galaxy. Whether as sources of rare materials, sites for advanced research, or even potential homes for future civilizations, planets born from the remnants of dead stars could play a crucial role in the next era of exploration. The idea that destruction could give rise to new worlds is a poetic one. Supernovae mark the violent deaths of massive stars, yet from their ashes, new possibilities emerge. The heavy elements that make up our own planet, and even our own bodies, were forged in ancient supernova explosions billions of years ago. If entire planets can form from this cosmic debris, it reinforces the idea that the universe is constantly renewing itself, transforming chaos into creation. And if that's true, then somewhere out there, drifting through the darkness of space or orbiting a distant star, there may be a planet unlike anything we've ever seen. A world built from the remains of a stellar explosion, holding the secrets of the cosmos within its strange and alien landscape. One day, we may find it. And when we do, it could change everything we know about the universe. The possibility of planets forming from supernova remnants is not just a theoretical exercise. It is a profound question that challenges our understanding of planetary formation, cosmic evolution, and even the potential for life beyond Earth. If such planets exist, they could be among the most extreme worlds in the universe, shaped by the violent aftermath of stellar explosions. But how exactly would these planets form, and what conditions would be required for them to emerge from the debris of a dying star? To understand this, we need to look at what happens during and after a supernova. When a massive star reaches the end of its life, it undergoes a catastrophic explosion, ejecting enormous amounts of material into space. This material includes both lighter elements like hydrogen and helium, as well as heavier elements like iron, nickel, and even gold and uranium. These elements are scattered across the surrounding region, mixing with the interstellar medium. The explosion also sends powerful shock waves that compress nearby gas clouds, triggering the formation of new stars and planetary systems. The key question is whether the ejected material from a single supernova could coalesce into a planet on its own, without mixing with other surrounding material. In typical planetary formation, dust and gas from a protoplanetary disk gradually come together under gravity, forming larger and larger bodies until planets emerge. In the case of a supernova remnant, the leftover material would need to undergo a similar process, but under much harsher conditions. One of the biggest challenges is the immense heat and radiation produced by the supernova itself. The explosion releases an incredible amount of energy, which ionizes and disperses much of the surrounding matter. For a planet to form, the material would need to cool down and condense, which could take thousands or even millions of years. Additionally, the expanding shockwave could push much of the debris too far away to ever come together again under its own gravity. However, if the supernova occurs in a dense enough environment, such as within a stellar nursery or a region with a high concentration of interstellar gas, it's possible that some of the ejected material could become gravitationally bound. If this happens, it could eventually settle into a stable orbit around a nearby star or even form a free-floating rogue planet, drifting through space without a host star. Another crucial factor is the presence of other forces that could help the material clump together. Magnetic fields, turbulence, and interactions with nearby stellar winds could influence the way particles aggregate. In some cases, small clumps of material could act as seeds, gradually attracting more mass until they form larger planetary bodies. Over millions of years, these small protoplanets could accumulate enough material to become fully fledged planets. One possible outcome is that planets formed from supernova remnants might have very different compositions compared to typical exoplanets. Instead of being rich in lighter elements, they could be composed primarily of heavy metals and radioactive isotopes. This would give them extreme densities and potentially unusual geologies. Some might even lack a traditional atmosphere, as their formation process may not have included enough lighter gases like hydrogen and helium. If such planets do exist, their internal structures could be radically different from anything we've seen before. A planet formed from supernova debris could have a core made almost entirely of iron and nickel, with a thick mantle of exotic heavy elements. If radioactive materials are abundant, the planet might generate its own heat from internal radiation, potentially keeping it warm even if it drifts through the cold darkness of interstellar space. This raises another fascinating question. Could a planet formed from supernova remnants have liquid water? On Earth, water is essential for life, and its presence depends on the right balance of temperature and atmospheric pressure. If a supernova-born planet retained enough heat internally, it might be able to sustain liquid water beneath its surface, much like Jupiter's moon Europa. Alternatively, if it remained in orbit around a star, it could develop conditions that allow for the presence of surface water, although its high metal content might result in extreme atmospheric conditions. The search for such planets is still in its infancy, but future space telescopes and planetary surveys could provide more clues. Astronomers are already looking for exoplanets with unusual compositions, and any discovery of a planet with an abnormally high metal content could point to a supernova origin. In the coming decades, missions designed to analyze exoplanet atmospheres and surface compositions might reveal the first evidence of these extraordinary worlds. If we do find them, they could reshape our understanding of how planets form and evolve. The idea that entire worlds could arise from the ashes of dying stars challenges the traditional model of planetary formation and opens up new possibilities for the diversity of planetary systems in the universe. It also deepens our appreciation for the cosmic cycle of creation and destruction, where even the most violent events can give birth to something new. And if one of these planets were close enough for us to study in detail, it might hold secrets that could change the course of scientific discovery. Could it be a frozen wasteland, rich in precious metals? Could it harbor unknown chemical processes, unlike anything seen before? Or could it, against all odds, be home to life that emerged in the aftermath of a cosmic explosion? The idea might sound like science fiction, but the universe has a way of surprising us. With each new discovery, we learn that the cosmos is more complex and mysterious than we ever imagined. And somewhere out there, hidden among the stars, there may be a planet unlike anything we've ever seen, a world born from fire and destruction, carrying the echoes of a dying star into the next era of the universe's history. If planets can indeed form from supernova remnants, they might represent one of the most extreme and unusual planetary classes in the universe. Unlike the Earth, which formed from a relatively calm protoplanetary disk over millions of years, these planets would emerge from an environment of sheer destruction, an explosion so powerful that it outshines entire galaxies for brief periods. But if they do exist, what would they look like? What kind of landscapes would they have? And could they ever support life? To understand these possibilities, we need to consider the physical characteristics of a planet born from a supernova. First and foremost, its elemental composition would be significantly different from most known planets. The explosion of a massive star creates and disperses heavy elements, meaning that any planet forming from this debris would likely be rich in iron, nickel, gold, and other metals. This would likely result in planets with extreme densities, possibly even exceeding those of the most massive rocky exoplanets discovered so far. A supernova-formed planet might also be unusually radioactive. Supernovae produce unstable isotopes that release energy as they decay, and if a newly formed planet contained significant amounts of these isotopes, it could generate its own internal heat for billions of years. This could lead to an intense geothermal environment, with molten metal seas, towering volcanoes, and an ever-changing surface shaped by ongoing geological activity. In some cases, the internal heat might be sufficient to maintain subsurface oceans, similar to Europa or Enceladus in our solar system. The atmosphere, if the planet has one, would depend on how much lighter material was available during its formation. Traditional planetary formation involves the capture of volatile elements like hydrogen, helium, and water vapor, but a supernova remnant may lack significant amounts of these gases. As a result, such planets might have incredibly thin or exotic atmospheres, possibly dominated by heavier gases like carbon dioxide, sulfur dioxide, or even vaporized metals. The sky on such a planet could be filled with swirling, metallic clouds, reflecting the eerie glow of a nearby neutron star or pulsar. Speaking of pulsars, another possibility is that some of these planets could form around neutron stars, the dense, rapidly spinning remnants left behind after a supernova. Astronomers have already discovered planets orbiting pulsars, known as pulsar planets, suggesting that planetary material can survive the immense forces at play in a supernova's aftermath. These pulsar planets experience extreme radiation, bombarded by high-energy particles and intense magnetic fields. If a planet formed from supernova remnants in this kind of environment, it might be one of the most inhospitable worlds imaginable. However, there's also a chance that some of these planets could exist in more stable conditions. If the debris from a supernova mixed with a nearby molecular cloud, a dense region of gas and dust where new stars and planets form, the heavy elements could blend with lighter materials. This could lead to the creation of planets that are more similar to Earth but with unique mineral compositions and unusual atmospheric properties. The idea of such planets raises another tantalizing question: could life arise on a world formed from supernova remnants? On Earth, life depends on a delicate balance of conditions, including liquid water, a stable atmosphere, and protection from harmful radiation. If a supernova-born planet had a thick enough atmosphere or strong magnetic field, it might be able to shield itself from cosmic rays and retain conditions suitable for life. In some scenarios, extremophiles, organisms that thrive in extreme environments, could evolve to withstand the high levels of radiation and metal-rich chemistry. Alternatively, if these planets formed in a stable orbit around a star, they could develop biospheres unlike anything seen before. Perhaps their high metal content would result in ecosystems with unusual chemical pathways, where organisms rely on metallic compounds instead of traditional organic molecules. If intelligent life ever arose on such a planet, their civilization might be technologically advanced in ways we can't even imagine, possibly due to the abundance of heavy metals making space travel and energy production more accessible. The search for supernova-born planets is still in its early stages, but upcoming space missions could provide crucial insights. Telescopes like the James Webb Space Telescope and future exoplanet surveyors might be able to detect planets with unusual compositions, hinting at their explosive origins. By analyzing the spectral signatures of exoplanet atmospheres and surfaces, astronomers may one day confirm the existence of these extreme worlds. If we do find them, they would challenge many of our assumptions about how planets form and evolve. They would also reinforce the idea that the universe is constantly recycling itself, that even in destruction, there is creation. The atoms that make up our own bodies were once forged in the hearts of dying stars, scattered across the cosmos before coming together to form Earth. If entire planets can arise from supernovae, then the cycle of cosmic rebirth is even more profound than we ever imagined. Imagine standing on the surface of one of these planets, looking up at a sky filled with the remnants of the supernova that gave birth to your world. The landscape around you might be alien and harsh, with jagged metallic mountains and glowing fissures venting radioactive heat. The air could be dense with heavy gases, swirling in complex chemical storms. But despite the extreme conditions, this world would be proof that even the most violent cosmic events can lead to new beginnings. Somewhere out there, beyond our reach, such planets may already exist, waiting for the day when humanity has the technology to find them, explore them, and perhaps even set foot on their surfaces. Until then, they remain one of the greatest mysteries of space, a reminder that the universe is full of surprises, waiting to be uncovered. If planets formed from supernova remnants do exist, their discovery would be one of the most groundbreaking moments in astronomy. It would mean that even the most violent and destructive forces in the universe can pave the way for new worlds, reshaping our understanding of planetary formation. But how would we actually detect these planets? What specific signs should astronomers look for, and how can we differentiate them from ordinary exoplanets? One of the biggest clues would be their composition. Since supernovae create and scatter heavy elements, planets formed from their debris would have an exceptionally high metal content. Most exoplanets we've discovered so far have compositions somewhat similar to Earth, with a mix of silicates, iron, and lighter elements. However, a supernova-born planet might be rich in rare metals like gold, platinum, uranium, and even radioactive isotopes. This could give it unique spectral signatures, essentially, a fingerprint of light that astronomers can analyze using telescopes like the James Webb Space Telescope. Another potential clue would be their location. If these planets form directly from a supernova's debris, they might be found in regions where supernovae have recently occurred, such as within supernova remnants. These remnants, like the Crab Nebula, are vast clouds of energized gas and dust left behind after a star's explosion. If a planet were detected within or near such a remnant, it would strongly suggest that it formed from the explosion itself. Alternatively, if these planets formed in the presence of a neutron star, the dense core left behind after a supernova, they might be detected orbiting these extreme objects. As we already know, pulsar planets exist, meaning that planetary material can survive in the aftermath of a supernova. However, pulsars emit intense radiation and powerful magnetic fields, so any planet orbiting them would need to be highly resilient. If such a planet had a thick atmosphere or strong magnetic field, it could potentially shield itself from the deadly radiation of its neutron star host. But this raises another intriguing possibility. Could life ever emerge on a planet orbiting a pulsar? At first glance, the idea seems impossible. The radiation levels would be lethal for most known forms of life, and the intense gravitational forces from the neutron star could create extreme tidal effects on the planet. However, life has surprised us before. Extremophiles, organisms that thrive in extreme environments on Earth, have shown that life can persist in places we once thought were completely uninhabitable. Perhaps, deep beneath the surface of a supernova-born planet, life could take root. If the planet had a thick enough crust, it could shield underground oceans or hydrothermal vents from radiation, creating a habitable refuge similar to environments found under the ice of Europa or Enceladus. Some scientists even speculate that exotic forms of life could evolve to harness radiation as an energy source, much like how plants use sunlight for photosynthesis. Of course, detecting life on these planets would be even more challenging than finding the planets themselves. Even in our own solar system, we struggle to determine whether subsurface oceans on Europa or Enceladus contain life. However, advances in telescopes and exoplanet research may eventually allow us to analyze the atmospheres of distant planets in unprecedented detail. If we ever detect unusual chemical signatures, such as unexpected ratios of oxygen, methane, or other biosignatures, it could hint at the possibility of life on one of these extreme worlds. Another fascinating question is what these planets would look like from the surface. Imagine standing on a world forged in the fires of a supernova, where the ground beneath your feet is infused with rare metals and radioactive elements. The landscape could be unlike anything we've ever seen: vast metallic plains, mountains of crystallized elements, and glowing fissures where radioactive decay heats the ground from within. If the planet had an atmosphere, it could be thick with exotic gases, creating surreal weather patterns dominated by metallic storms and clouds of vaporized heavy elements. The sky above might be even stranger. If the planet orbits a neutron star, its day and night cycle could be completely different from what we experience on Earth. Pulsars rotate incredibly fast, sometimes hundreds of times per second, meaning the sky might flash with pulses of radiation at regular intervals. If the planet is in a binary system with another star, it could experience dual sunsets, with one star slowly sinking below the horizon while the neutron star continues to blaze with its relentless energy. If such planets exist, could they ever be colonized by humans in the far future? The idea of settling on a planet formed from a supernova is both thrilling and terrifying. The extreme conditions, high radiation, toxic atmospheres, and possibly unstable geology, would make survival incredibly difficult. However, advanced technology, such as radiation shielding and underground habitats, could potentially allow humans to establish outposts on these worlds. One major advantage of these planets could be their immense mineral wealth. Since supernovae create heavy elements, these worlds might be rich in valuable resources like gold, platinum, and even rare isotopes useful for advanced energy production. If humanity expands into space and begins interstellar mining, supernova-born planets could become some of the most sought-after destinations in the galaxy. But before we can dream of setting foot on one of these planets, we first need to prove they exist. Current exoplanet detection methods, such as the transit method and radial velocity measurements, are improving rapidly. In the coming decades, new telescopes and space missions could finally uncover evidence of these elusive worlds. If we find them, it would revolutionize our understanding of planetary formation and prove that even the most violent cosmic events can lead to new beginnings. The idea that planets could arise from the ashes of a dead star is a powerful reminder of the cyclical nature of the universe. Stars are born, they live, they die in spectacular explosions, and yet, even in death, they create the building blocks for new worlds. Our own solar system was shaped by the remnants of ancient supernovae, meaning that, in a way, we ourselves are products of these cosmic explosions. If planets can form directly from supernova remnants, it would be one of the greatest discoveries in the history of astronomy, proof that the universe is far more resilient and creative than we ever imagined. These planets, forged in fire and destruction, could hold secrets about the nature of matter, the potential for life, and the endless possibilities of the cosmos. Somewhere out there, among the shattered remains of long-dead stars, these worlds may already exist, waiting to be found. And when we finally uncover them, they will challenge everything we thought we knew about the universe. The discovery of planets formed from supernova remnants would be more than just a scientific breakthrough. It would redefine our understanding of how planetary systems emerge from destruction. But if such planets exist, how many could be out there? Could they be common across the galaxy, or are they just a rare anomaly? To answer this, we have to consider the sheer number of supernovae that have occurred throughout cosmic history. In the Milky Way alone, astronomers estimate that a supernova explosion happens roughly once every 50 years. That means in the past billion years, millions of supernovae have rocked our galaxy, scattering their enriched elements into space. If even a small percentage of these explosions led to planet formation, there could be countless planets forged in the aftermath of stellar death, hidden among the stars. One way to estimate their prevalence is by looking at the number of known pulsar planets. Since we've already discovered exoplanets around pulsars, objects that survive the supernova process, it suggests that planetary formation in these extreme environments isn't impossible. But planets formed directly from the debris field of a supernova could be different. Unlike pulsar planets, which might have been captured or survived the explosion, these planets would have assembled from the raw materials left behind. The composition of these planets could provide an essential clue to their origins. Unlike typical exoplanets, which form from a protoplanetary disk around a young star, supernova-born planets would likely have an abundance of heavy elements. This means they could have an unusually dense core, a thick metallic crust, and a unique mineralogical makeup. Some scientists speculate that such planets might even contain exotic materials not commonly found in planets that form through traditional means. Imagine a world where the surface is littered with rare, crystallized metals, where entire mountain ranges are composed of elements like platinum, tungsten, or even radioactive isotopes like uranium. The presence of these elements could mean that these planets have unusual magnetic fields or even internal heat sources powered by radioactive decay. This could make them geologically active, with intense volcanism, earthquakes, and possibly even subsurface oceans of liquid metal rather than water. If these planets exist, what would their atmospheres look like? Traditional planets often have atmospheres formed from lighter elements like hydrogen, helium, nitrogen, and oxygen. But a planet formed from supernova remnants could have a completely different atmospheric composition, with heavy gases like xenon, radon, or even vaporized metallic elements. Depending on the environment, these atmospheres could be toxic, corrosive, or electrically charged due to interactions with strong magnetic fields. This could create some of the most extreme weather conditions imaginable. Instead of water rain, these planets might experience metal storms, clouds of vaporized iron or silicon that condense and fall as molten droplets, reshaping the landscape over time. Winds could carry electrically charged particles, creating constant lightning storms that illuminate the skies in a terrifying display of cosmic energy. And what about their potential habitability? Life, as we know it, might struggle to survive in such an environment, but that doesn't mean all life would be impossible. If extremophiles on Earth can thrive in radioactive environments, acidic lakes, and deep-sea hydrothermal vents, then perhaps life could find a way even on these worlds. However, it would have to be radically different from anything we're familiar with. One possibility is that life on these planets could evolve to use radiation as an energy source instead of sunlight. Some theoretical models suggest that certain types of bacteria could develop protective biofilms, or even use radiation harnessing processes similar to photosynthesis. If such life exists, it would be unlike anything on Earth, adapted to an existence where high-energy particles bombard the environment constantly. But what if intelligent life evolved on one of these worlds? If a civilization developed in such an extreme place, their entire understanding of physics, chemistry, and survival would be shaped by the unique conditions of their home planet. Their technology might be radically different from ours, perhaps relying on exotic materials or forms of energy that we have yet to comprehend. If we ever make contact with such a civilization, their perspective on the universe could be utterly alien to us. They might see radiation as a resource rather than a danger, metal-rich environments as the norm rather than the exception, and traditional habitable planets like Earth as strange, water-covered anomalies. Their biology, culture, and technology could be so fundamentally different that communication itself might be a challenge. But before we speculate on alien civilizations, we need to find the planets themselves. How close are we to detecting them? Modern telescopes, like the James Webb Space Telescope, are already capable of analyzing exoplanet atmospheres and compositions with incredible detail. Future missions could focus specifically on supernova remnants, searching for planets hidden within the expanding debris clouds of ancient stellar explosions. One potential detection method is through gravitational microlensing, a phenomenon where the gravity of an unseen object bends and magnifies the light of a background star. If a planet formed from a supernova remnant passes in front of a distant star, its gravitational influence could reveal its presence. This method has already been used to detect rogue planets, worlds that don't orbit any star, and it could be key in uncovering supernova-born planets as well. Another approach involves searching for planets around known neutron stars. If a pulsar has planets, those planets could have formed in the aftermath of the supernova that created the neutron star. By analyzing their orbits, compositions, and potential atmospheres, astronomers could determine whether these planets formed from pre-existing material or directly from the explosion's debris. The more we study supernova remnants, the better our chances of finding these planets. And when we do, the implications will be enormous. Not only will it prove that planets can arise from destruction, but it will also challenge our assumptions about planetary formation, habitability, and the diversity of worlds in the universe. The idea of planets forming from supernova remnants isn't just a theoretical possibility. It's a testament to the incredible resilience of the cosmos. The universe isn't just a place of chaos and destruction. It's also a place of rebirth, where even the most violent events can lay the foundation for new worlds. Perhaps one day, we'll discover a planet orbiting a neutron star, its surface glowing faintly from radioactive decay, its skies filled with exotic, electrified clouds. Perhaps it will have strange weather, an alien atmosphere, or even the first hints of life in the most unexpected of places. And when we finally uncover these worlds, we'll know for certain that the universe is far more creative and far more mysterious than we ever imagined. If we do discover planets formed from supernova remnants, the next big question will be, how do they evolve over time? Traditional planets undergo significant changes due to geological activity, atmospheric shifts, and interactions with their parent stars. But supernova-born planets might experience an entirely different evolutionary path, shaped by the extreme conditions in which they formed. One of the biggest factors influencing their evolution would be their exposure to intense radiation. Since these planets emerge from the aftermath of a supernova, they would likely start their existence bathed in high-energy particles, gamma rays, and X-rays. This radiation could strip away any early atmospheres, leaving behind barren, metallic surfaces. However, over time, if the planet retains a strong magnetic field or develops a secondary atmosphere from volcanic outgassing, it could become more stable. The cooling process of such a planet would also be unique. In typical planetary formation, heat is generated from gravitational compression, radioactive decay, and impacts from leftover debris. But in a supernova-born planet, the initial heat source would be much more intense. Some of these planets might even begin as molten worlds, glowing like miniature stars before gradually cooling over thousands, or even millions of years. Their surfaces could solidify into thick, mineral-rich crusts, potentially creating some of the densest planets in the universe. Another fascinating possibility is that these planets could end up as rogue planets, worlds that don't orbit a star. Supernovae are incredibly violent, and the force of the explosion can eject planets from their systems, sending them hurtling through interstellar space. If a planet formed from supernova remnants was given just enough of a push, it might become a wandering world, floating alone in the darkness. Rogue planets are some of the most mysterious objects in the universe. Without a star to provide heat, these planets rely entirely on internal energy sources. Some might have thick atmospheres that trap residual heat, while others could have subsurface oceans insulated by layers of ice. If a supernova-born planet ended up as a rogue planet, its history would be even more dramatic. It would have emerged from the explosive death of a star, only to be cast out into the void, drifting endlessly through space. Could such a planet ever be habitable? It seems unlikely, given the extreme conditions. But life has a way of surprising us. Some scientists have suggested that life could exist deep underground on rogue planets, where geothermal heat provides enough warmth for liquid water to exist. If a supernova-born planet retained radioactive elements in its core, it might generate enough heat to sustain a hidden biosphere beneath its surface. This raises another mind-bending question: what if intelligent life evolved on one of these planets? A civilization on a rogue planet wouldn't have a sun in the sky, meaning they wouldn't develop a concept of day and night as we understand it. Instead, they might rely on bioluminescence, geothermal energy, or other non-stellar sources of light. But let's take a step back and consider what it would take to actually confirm the existence of these planets. Astronomers would need to look in the right places, specifically at young supernova remnants where planets could still be forming. They'd have to study the movement of dust and gas, searching for clumps that could be early-stage planetary embryos. Advanced telescopes, like the upcoming Extremely Large Telescope, ELT, and future space observatories, might finally have the resolution needed to detect these hidden worlds. There's also the possibility of discovering indirect evidence. If we detect strange chemical signatures in a supernova remnant, unusual concentrations of metals, unexpected molecular compounds, it could hint at planet formation. The key would be distinguishing between leftover debris and actual planetary bodies, which would require extremely detailed spectral analysis. And what if we actually find one? The confirmation of a planet formed from supernova remnants would revolutionize planetary science. It would force astronomers to rethink the entire life cycle of planets, proving that planetary formation isn't limited to traditional protoplanetary disks. It would show that planets can emerge from destruction, forging themselves in the chaotic aftermath of stellar death. But beyond the scientific implications, the discovery would also challenge our philosophical understanding of the universe. It would be a reminder that even in the most violent and catastrophic events, new possibilities arise. The same explosion that destroys a solar system could also create the building blocks for something new, a planet unlike any other, waiting to be found. And maybe, just maybe, one day we'll send a spacecraft to explore one of these worlds. It could land on a surface of solid metal, beneath a sky filled with charged storms, and uncover secrets that rewrite everything we thought we knew about planets. Until then, the mystery remains. If we do find a planet formed from supernova remnants, what would it actually look like? Would it resemble the rocky worlds in our solar system, or would it be something entirely alien? Given the extreme conditions under which it would have formed, it's likely that such a planet would be vastly different from anything we've ever seen. For starters, its composition would be unusual. Unlike planets that form in traditional protoplanetary disks, which primarily contain hydrogen, helium, and other common elements, a planet formed from a supernova remnant would be rich in heavier elements like iron, nickel, and even exotic radioactive materials. This could make it incredibly dense, potentially even denser than the most metal-rich exoplanets we've discovered so far. Some of these planets could be almost entirely composed of iron, with only a thin layer of rock or other materials on their surfaces. A planet like this might also have an incredibly strong magnetic field. The abundance of iron and nickel in its core, combined with the rapid cooling process it would undergo, could create a dynamo effect far more intense than what we see on Earth. This could lead to powerful auroras lighting up its sky, even without a nearby star. Charged particles left over from the supernova could still be interacting with the planet's magnetosphere, creating a world where the sky is constantly filled with shifting, glowing lights. Its surface might be covered in unusual minerals and elements rarely found in our solar system. Supernovae produce some of the rarest and heaviest elements in the universe, including gold, platinum, and uranium. If these elements were incorporated into the planet's crust, it could be one of the richest celestial bodies in terms of valuable resources. Imagine a planet where entire mountain ranges are made of precious metals, or where radioactive elements naturally glow in the dark, casting an eerie light across the landscape. The presence of these heavy elements could also mean that some of these planets generate their own internal heat for billions of years. Radioactive decay in the planet's core could keep its interior warm long after its formation, potentially sustaining underground oceans or even volcanic activity. This means that even if the planet is far from any star, or completely alone as a rogue planet, it might still have liquid water beneath its surface. The idea of a planet formed from supernova remnants also raises questions about how its atmosphere, if it has one, would develop. If the planet had enough gravity to hold onto gases, it might slowly accumulate an atmosphere over time from volcanic outgassing or from interactions with the interstellar medium. But what would this atmosphere be made of? It's possible that, instead of the nitrogen-oxygen mix we're familiar with, the air on this planet could be full of exotic gases like neon, argon, or even trace amounts of elements we don't usually see in planetary atmospheres. This leads to an even more fascinating question. Could such a planet ever support life? If it formed in the right conditions, retained enough heat, and developed some kind of stable atmosphere, it might not be completely inhospitable. Life, as we know it, thrives in all kinds of extreme environments: acidic lakes, deep-sea hydrothermal vents, and even inside solid rock. If life somehow emerged on a planet born from a supernova, it would have to be incredibly resilient, capable of surviving in a world full of heavy radiation, extreme temperatures, and potentially toxic chemicals. But here's where things get even stranger. What if life didn't just survive on this planet? What if it was actually seeded by the supernova itself? Some scientists believe that supernovae could play a role in spreading the building blocks of life across the universe. When a massive star explodes, it sends out shockwaves that compress nearby clouds of gas and dust, triggering star and planet formation. If organic molecules or even primitive life forms were present in that dust, they could be carried to newly forming planets, including those made from the supernova's own remnants. This means that a planet formed from a supernova might not just be a world of death and destruction. It could also be a world of creation, a place where the very elements forged in a dying star come together to form something entirely new. Imagine a planet where life emerges in the ruins of an explosion, evolving under conditions unlike anything we've ever encountered. It might not look like life on Earth. It might be based on completely different chemistry, using elements that are rare in our own biosphere. Could intelligent life evolve in such a place? It's difficult to say, but if it did, its entire understanding of the universe would be different from ours. It wouldn't have a sun to orbit. It might not even have a clear distinction between day and night. Instead, its civilization might be built around geothermal energy, underground habitats, or even artificial sources of light and heat. And what if, after billions of years, they looked up at the sky and wondered if they were alone? If their planet had been ejected into interstellar space, drifting alone in the darkness, they might not even know that stars existed. They might think that all of existence was just their single, lonely world. Until one day, perhaps, they detect a distant light, a star far away, shining through the void. This is the kind of mystery that keeps scientists searching. If planets can form from supernova remnants, then the universe is even more unpredictable and chaotic than we imagined. But it also means that even in destruction, new possibilities arise. The same explosion that obliterates one world could be the spark that creates another. And maybe, just maybe, somewhere out there, a planet born from a dead star is waiting to be found. If a planet formed from the remnants of a supernova, what would its journey through the cosmos look like? Would it remain close to the region where the explosion occurred, or would it be flung into the depths of interstellar space, becoming a rogue planet drifting in the cold, endless void? One of the most fascinating possibilities is that these planets might not remain bound to their original locations. When a star explodes in a supernova, the sudden release of energy and matter can disrupt the entire system around it. If the star had planets before the explosion, they might either be vaporized, ejected into space, or absorbed into the forming nebula. But in the case of newly formed planets, those that arise from the supernova debris, they might have no stable gravitational anchor. Without a central star to orbit, they could be launched into interstellar space as rogue planets. Rogue planets are some of the most mysterious objects in the universe. Unlike traditional exoplanets, which orbit stars and can be detected through their interactions with starlight, rogue planets wander alone. These worlds could be scattered everywhere, hidden in the darkness, nearly impossible to detect. If planets do form from supernova remnants, there might be entire populations of these orphaned worlds floating between the stars, each carrying with it the history of a stellar catastrophe. But could these rogue planets sustain any kind of activity? Surprisingly, the answer might be yes. While they wouldn't have a nearby star to provide warmth, they might still retain internal heat from radioactive decay, left over from the explosion that created them. Some scientists believe that rogue planets could have subsurface oceans, kept liquid by geothermal energy. If this is the case, then even in the loneliest corners of space, there could be pockets of liquid water, one of the key ingredients for life as we know it. Imagine an entire network of these planets, drifting unseen through the galaxy, each a silent witness to the death of the star that gave birth to it. Some might have thick, insulating atmospheres trapping heat, keeping their surfaces relatively warm despite the cold of space. Others might be covered in frozen ice, with only deep underground layers remaining warm enough for liquid water. And some might be nothing more than barren, lifeless husks, composed mostly of heavy metals and radioactive isotopes, still cooling from the violent energy of the supernova that formed them. This idea also raises another possibility. Could we ever find one of these planets? Detecting rogue planets is already difficult, as they don't pass in front of stars the way traditional exoplanets do. But if a planet formed from supernova debris, it might contain unique chemical signatures, traces of elements that wouldn't normally be found in planets formed in standard protoplanetary disks. If astronomers were to analyze the composition of a rogue planet and find an unusual abundance of heavy elements, it could be evidence that the planet originated from a supernova explosion. Some researchers speculate that future space telescopes might be able to spot these worlds using infrared imaging, detecting the faint heat they still emit from their formation. If we could find even one of these planets, it would provide an entirely new perspective on planet formation. It would prove that planets can form in environments far more extreme than we ever imagined, and that the cycle of destruction and creation in the universe is even more complex than we thought. And then there's the ultimate question: could Earth itself have remnants of a supernova in its past? While our planet formed in a relatively stable protoplanetary disk, some scientists believe that parts of our solar system, including elements found in our own crust, may have been seeded by ancient supernovae. It's possible that long before the Sun and planets formed, a massive star exploded nearby, enriching the region with heavy elements. If this is true, then in a way, we are all made from the remnants of a supernova, not in the sense of a whole planet forming directly from an explosion, but in the sense that the very materials that make up our world were once forged in the heart of a dying star. This brings us to an even deeper mystery. If life can emerge on a world like Earth, which was enriched by supernova elements, could it also arise on a planet that formed entirely from those remnants? The idea of life on such a planet seems almost impossible at first. After all, these planets would be exposed to extreme radiation, bathed in heavy elements, and potentially frozen in deep space. But the universe has repeatedly shown us that life is capable of surviving in conditions we once thought were completely inhospitable. On Earth, we've discovered organisms that thrive in radioactive environments, in the crushing depths of the ocean, and even inside solid rock. If similar organisms could develop on a planet formed from supernova remnants, they might be some of the most resilient forms of life in the universe. Perhaps they would evolve to harness radioactive decay for energy, similar to how plants on Earth use sunlight. Maybe they would develop biological structures unlike anything we've ever seen, adapted to withstand extreme conditions that would destroy life as we know it. And what if, in the distant future, humanity were to encounter one of these worlds? Would we recognize it for what it is, a relic of a stellar explosion, a planet forged from destruction? Would we find it barren, or teeming with strange and unfamiliar life? The possibility of discovering a planet that formed from the ashes of a dead star is one of the most exciting frontiers of astronomy, and it's a reminder that the universe is far from predictable. The mystery of whether planets can form from supernova remnants is not just a question about planetary science. It's a question about the nature of creation itself. It challenges our understanding of how planets come into being, how matter is recycled through the cosmos, and whether life can emerge from the most unexpected places. And perhaps most intriguingly, it suggests that even in the aftermath of the most violent events in the universe, new worlds can be born. Somewhere out there, in the vast and silent depths of space, a planet formed from a supernova may be waiting to be discovered. It may be drifting alone, untouched for billions of years, a frozen monument to the star that once existed before it. Or it may be something else entirely, an active, living world, proving that even the greatest cosmic catastrophes can lead to new beginnings. The idea that planets could form from supernova remnants is more than just a wild hypothesis. It's a direct extension of what we already know about how elements spread through the universe. Every atom in our bodies heavier than hydrogen and helium was forged in a star, and some of the heaviest ones, like gold, uranium, and platinum, were created in supernovae or even more extreme events like neutron star mergers. But while we know these elements get scattered into space, the next question is whether they can actually coalesce into something as complex as a planet. The process of planetary formation from supernova debris would be vastly different from the formation of planets in a traditional protoplanetary disk. In a normal planetary system, a star forms first, pulling a vast disk of gas and dust into orbit around it. Over time, this material clumps together to form planets. But in the case of a supernova, the explosion itself would initially blow everything apart. The intense shock waves would send material speeding outward at incredible velocities, dispersing heavy elements into interstellar space. So how could a planet ever emerge from such chaos? One possibility is that the expanding debris from a supernova might eventually slow down and cool enough for clumps of material to begin forming. If these clumps are large enough, they could attract more matter through gravity, eventually becoming planet-like bodies. This wouldn't happen immediately after the explosion. The process could take millions of years, requiring the surrounding interstellar medium to interact with the debris and slow it down. Another scenario involves a nearby molecular cloud, a region of cold gas and dust in space, capturing the heavy elements from a supernova and using them as raw materials for planet formation. Instead of forming directly within the supernova remnants, the elements ejected from the explosion would mix with pre-existing gas clouds, enriching them with the ingredients needed for rocky planets. This could explain why some planets, including Earth, contain elements that only form in supernovae. But what about planets that form directly from the densest parts of the supernova debris? There's some evidence that such objects might exist. Astronomers have discovered objects known as pulsar planets, planets that orbit the remnants of dead stars, such as neutron stars or pulsars. These planets are incredibly unusual because they shouldn't exist in such extreme environments. The stars they orbit went through violent supernova explosions, which should have destroyed or ejected any existing planets. The fact that pulsar planets exist at all suggests that new planetary formation can happen even in the wake of a supernova. One of the most famous examples is Pulsar B1257+12, a pulsar located about 2,300 light-years away in the constellation Virgo. This pulsar has at least 3 confirmed planets orbiting it, and they're believed to have formed after the star exploded. Instead of being remnants of a pre-existing planetary system, they may have formed from the material left behind after the supernova. This discovery is one of the strongest pieces of evidence that planets can indeed form from the remnants of an exploded star. If planets can form around neutron stars, what about black holes? When a massive star goes supernova, it can sometimes leave behind a black hole instead of a neutron star. This raises the possibility that planets could form in orbit around black holes, or even that planets could be captured by black holes from interstellar space. Some researchers have even speculated about the existence of habitable planets orbiting black holes, worlds where the energy needed to sustain life comes from the radiation and gravitational interactions surrounding the black hole rather than from a traditional star. But even without black holes in the picture, the idea of planets forming from supernova debris leads to some incredible questions. Could a planet that forms this way ever develop conditions suitable for life? Traditional planet formation models assume a long, stable process where a planet gradually accumulates material and evolves over billions of years. A planet that forms from supernova remnants would have a much more violent and unpredictable origin. It might be loaded with radioactive elements, exposed to intense radiation, and subject to extreme temperatures. Yet, some planets in our own solar system have gone through extreme conditions and still developed complex geological features. Take Io, for example, one of Jupiter's moons. Io is constantly being torn apart by Jupiter's gravity, leading to non-stop volcanic activity. Its surface is covered in lava lakes and massive eruptions. If a moon like Io can exist in such a brutal environment, then perhaps a planet that forms from supernova debris could stabilize over time. Another factor to consider is magnetism. Supernovae produce incredibly strong magnetic fields, and if a planet formed directly from a supernova's remnants, it might have a much stronger magnetic field than Earth. A powerful magnetic field could help protect the planet from radiation, making it more habitable than it might otherwise be. If such a planet had an atmosphere, a strong magnetic field could also help shield it from solar winds or cosmic rays. This brings us back to one of the most intriguing possibilities. What if planets formed from supernova remnants exist all over the universe, but we just haven't found them yet? The problem with detecting such planets is that they wouldn't necessarily be orbiting normal stars. If they formed around neutron stars or pulsars, they would be incredibly difficult to detect with traditional exoplanet hunting methods. If they became rogue planets, drifting through space with no star to illuminate them, they would be nearly invisible. However, future telescopes, like the James Webb Space Telescope and its successors, might be able to detect these worlds by looking for faint thermal emissions. Even if a planet has no star, it could still emit a small amount of infrared radiation, especially if it retains heat from its formation. Another way to find them might be through gravitational microlensing, an effect where a massive object passing in front of a distant star bends and magnifies the star's light. If we do find a planet that formed from supernova remnants, it would rewrite our understanding of planetary formation. It would show that planets don't need to emerge from the calm, swirling disks around young stars. Instead, they can arise from destruction, from the fiery deaths of massive stars. It would mean that even in the wake of the most violent events in the universe, new worlds can be born. And if we find one of these planets, what might it look like? Would it be a scorched wasteland, covered in the scars of its violent birth? Would it be rich in heavy elements, filled with exotic minerals and radioactive compounds? Could it even have life, strange, resilient organisms that evolved in an environment unlike anything we've ever seen? The search for planets formed from supernova remnants is still in its early stages, but the implications are profound. It means that the universe is even more unpredictable than we thought. It means that planets can emerge in places we never expected. And it means that somewhere, hidden among the stars, there could be entire worlds forged from the ashes of dying suns. If planets can form from supernova remnants, the implications extend far beyond just planetary science. It would fundamentally alter our understanding of the life cycle of matter in the universe. Normally, we think of the death of a star as the end of a system, the final chapter of a celestial body's existence. But what if, instead of an ending, it's actually a new beginning? What if supernovae, rather than simply being destructive forces, are also responsible for creating entirely new planetary systems? To fully grasp this possibility, we need to look at the mechanics of a supernova explosion. When a massive star reaches the end of its life, it can no longer sustain nuclear fusion in its core. The outward pressure that once counteracted gravity collapses, causing the star to implode before violently exploding outward. This explosion releases an enormous amount of energy, sometimes outshining an entire galaxy for a brief period, and sends heavy elements hurtling into space. This ejected material, known as a supernova remnant, consists of gas, dust, and newly formed elements like iron, nickel, gold, and even uranium. Over thousands to millions of years, these remnants interact with the surrounding interstellar medium, enriching it with complex chemical compounds. If this material encounters a molecular cloud, a dense region of gas and dust, it could trigger a new wave of star and planet formation. This process is sometimes called triggered star formation, and it suggests that the death of one star can lead to the birth of many more. But could a planet form directly from the supernova remnant itself, without needing a molecular cloud? That's where things get interesting. Some scientists speculate that if a supernova explosion occurs in a particularly dense region of space, the ejected material might not disperse completely. Instead, some of it could gravitationally recollapse into clumps, forming planet-like bodies. These objects would likely be very different from Earth-like planets. They might have high concentrations of heavy metals, extremely strong magnetic fields, and unusual atmospheres filled with exotic gases. One of the biggest challenges for a planet forming in such an environment is stability. Supernova remnants are incredibly turbulent, filled with shock waves and high-energy radiation. Any clump of material trying to form into a planet would need to resist being torn apart by these violent forces. However, if the explosion's energy dissipates quickly enough, and if the remnant is dense enough, localized regions of relative calm could form. In these pockets, heavier elements could start to accumulate, leading to the birth of a new planetary body. Interestingly, this might help explain certain types of rogue planets, planets that don't orbit any star. These free-floating worlds could be the result of planetary formation within supernova remnants. Instead of forming around a young star, they might have formed independently in the aftermath of an explosion and simply drifted through space ever since. If this is true, then rogue planets could be far more common than we currently realize. Detecting such planets is extremely difficult. Traditional exoplanet detection methods, like the transit method, which looks for dips in a star's brightness as a planet passes in front of it, wouldn't work for planets that don't orbit stars. Instead, scientists rely on gravitational microlensing, where a rogue planet's gravity bends and magnifies the light of a distant star behind it. This technique has already provided evidence for the existence of free-floating planets, though whether any of them formed directly from supernova remnants remains unknown. If we could study one of these planets up close, what would we find? Would it have a solid surface, or would it be a gas-dominated world with extreme temperatures? Would it have an atmosphere, or would it be a barren wasteland exposed to the harshness of interstellar space? One of the most fascinating possibilities is that these planets could have entirely unique geological compositions. Since supernovae produce a wide range of heavy elements, a planet forming from this material might have far more gold, platinum, or even radioactive elements than planets like Earth. Its crust might be rich in rare minerals that don't commonly occur on Earth. Its internal heat could be powered by radioactive decay at levels far beyond what we see in our own planet's core. If such a planet had any liquid components, such as lava or even a strange form of liquid metal, it could exhibit exotic chemistry unlike anything we've ever seen. And then there's the question of life. Could a planet born from a supernova sustain any kind of living organisms? On the surface, it seems unlikely. The early conditions of such a planet would be extremely hostile: high radiation, rapid cooling, and possibly a lack of stable surface conditions. However, life has a way of surprising us. Extremophiles on Earth thrive in environments once thought uninhabitable, from the crushing pressures of deep-sea hydrothermal vents to the frozen deserts of Antarctica. If life found a way to emerge on a planet formed from a supernova remnant, it would likely be unlike anything we could imagine. Perhaps it would be based on completely different biochemistry, relying on elements and compounds rare in traditional planetary systems. It might have adapted to survive extreme radiation levels, using novel DNA structures or alternative molecular building blocks. If such life existed, it would redefine our understanding of biology and expand our search for habitable worlds beyond the usual parameters. Another possibility is that these planets could act as stepping stones for life rather than cradles of origin. If a planet formed from supernova remnants eventually drifted into a more stable region of space, it might later capture an atmosphere, develop conditions suitable for life, or even be colonized by microbial life from other celestial bodies. This raises the question of whether some rogue planets, possibly born from supernovae, could eventually become habitable as they evolve over billions of years. In essence, the idea that planets could form from supernova remnants challenges our traditional views of planetary formation. It suggests that destruction and creation are deeply intertwined, that the death of one star could directly lead to the birth of new worlds. It hints at a universe where planets can form in places we never expected, from material we once thought was simply scattered into the void. And perhaps, somewhere out there, in the vast expanse of interstellar space, a world forged from the ashes of a dying star is waiting to be discovered. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.